In the year 1054, a star exploded in a blaze of light so bright it could be seen during the day. This wasn't just any cosmic event. It was the birth of the Crab Nebula, a region of space that continues to baffle and inspire scientists to this day. What if I told you this massive explosion, recorded by ancient astronomers, holds clues to 50 strange phenomena that defy our understanding of the universe? From mysterious pulsar winds that sculpt the nebula to gamma-ray flares that challenge our knowledge of physics, this cosmic wonderland is packed with secrets just waiting to be uncovered. In this video, we're diving deep into the heart of the Crab Nebula, exploring its twisted magnetic fields, supercharged particles, and even dust grains that survive in one of the harshest environments imaginable. By the end of this journey, you'll see why this celestial spectacle is more than just a beautiful sight. It's a living laboratory for understanding the mysteries of space. So buckle up as we embark on a cosmic adventure through 50 bizarre and fascinating phenomena that continue to reshape our understanding of the universe. Keep watching because you won't want to miss a single discovery. Now that we've set the stage for our cosmic journey, let's zoom in on the powerhouse at the heart of the Crab Nebula. At its core lies a pulsar, a rapidly spinning neutron star that acts like a cosmic lighthouse, emitting beams of radiation. But this isn't just any pulsar. It generates something truly extraordinary: high-energy winds that stretch far beyond the star itself. These winds, made up of charged particles moving at nearly the speed of light, are anything but ordinary. They carve through the surrounding material, shaping the nebula into the intricate structure we see today. Think of it like a cosmic artist at work, sculpting glowing clouds with invisible hands. But here's the fascinating part: these pulsar winds don't just create beauty. They also challenge scientists to rethink how energy moves and interacts in space. When the winds collide with the nebula's material, they produce shock waves that release immense amounts of energy, fueling phenomena like X-rays and gamma rays. This interplay between the pulsar winds and the nebula gives us a front-row seat to study some of the universe's most extreme physics. So, as we peel back the layers of this mystery, keep in mind that these winds aren't just shaping the Crab Nebula, they're reshaping how we understand the universe's most powerful forces. Next, we'll explore an even stranger effect tied to these winds: the illusion of faster-than-light motion, a concept that will truly bend your perception of reality. So stay tuned, because the journey is just getting started. As we venture deeper into the enigmatic heart of the Crab Nebula, another mind-bending phenomenon comes into view, one that seems to defy the very laws of nature. This is the baffling observation of what appears to be faster-than-light motion, a cosmic illusion created by jets shooting out from the pulsar. Now, before you start questioning the limits of physics, let's break this down. These jets are not actually breaking the universal speed limit set by Einstein's theory of relativity. Instead, what we're witnessing is a trick of perspective, a cosmic sleight of hand that plays with how we perceive motion across vast distances in space. Picture this: imagine standing on a train platform as a train speeds past you. If the train is moving fast enough and your position just right, it might seem like it's covering enormous distances in the blink of an eye. In a similar way, the jets emitted from the pulsar appear to outpace light itself when viewed from certain angles, thanks to their incredible speed and the geometry of their trajectory. Scientists call this superluminal motion, and while it sounds otherworldly, it's entirely consistent with our understanding of physics when examined closely. Observations from telescopes like the Hubble Space Telescope have captured this phenomenon in stunning detail, showing blobs of material in the jets traveling at speeds that seem to exceed light speed. What's even more intriguing is how these jets challenge astronomers to rethink their assumptions about celestial mechanics. By studying these apparent violations of physics, researchers gain deeper insights into the nature of space, time, and the behavior of matter under extreme conditions. And here's the kicker. These jets aren't just fascinating quirks of the universe, they're also key players in shaping the Crab Nebula's energetic environment. They interact with surrounding magnetic fields, generate shock waves, and contribute to the dazzling emissions we observe across the electromagnetic spectrum. Just when you thought the Crab Nebula couldn't get any stranger, it throws us another curveball, one that invites us to question and marvel at the intricacies of the cosmos. But the mysteries don't stop here. Up next, we'll dive into an explosive revelation: gamma-ray flares that erupt from the nebula, leaving scientists puzzled about their origins and implications. So, buckle up as we continue unraveling the secrets of this celestial wonder. Just when you think the Crab Nebula has revealed all its secrets, it unleashes yet another cosmic surprise: gamma-ray flares. These explosive bursts of energy are among the most perplexing phenomena ever detected in the nebula, and they've left scientists scratching their heads for years. To truly appreciate their strangeness, we need to rewind to their discovery. It all began with observatories like the Fermi Gamma Ray Space Telescope, which first picked up these intense flashes of high-energy radiation. What made them so shocking was their sheer power. Gamma-ray flares from the Crab Nebula can outshine even its usual output, which is already one of the brightest sources in the sky. But here's the real puzzle. According to our current models of pulsars, this shouldn't be happening. Pulsars are known for their steady energy emissions, so why does the Crab Nebula's pulsar occasionally erupt in these unpredictable, ultra-bright flares? Researchers have been working tirelessly to find answers, and several theories have emerged. One possibility is that the flares are caused by sudden rearrangements in the pulsar's magnetic field. Picture a tightly coiled spring snapping into a new configuration. This kind of magnetic reconnection could release an enormous amount of energy in the form of gamma rays. Another idea suggests that these flares might be linked to turbulence within the nebula's plasma, where chaotic interactions could generate shock waves capable of accelerating particles to extreme energies. Yet, no single explanation fully accounts for the scale and unpredictability of these events. What makes gamma-ray flares even more baffling is that they don't follow a regular pattern. Some flares last mere hours, while others stretch on for days, and their intensity can vary wildly. This randomness challenges our understanding of pulsars and raises new questions about the conditions needed to produce such extreme bursts of radiation. The implications are huge. These flares could offer a window into processes that occur under the most extreme conditions in the universe, helping us refine our models of particle acceleration and high-energy physics. But as fascinating as these flares are, they also highlight just how much we still don't know about the Crab Nebula. Every observation brings us closer to unraveling its mysteries, but with each discovery comes a fresh wave of questions. And speaking of questions, the next part of our journey takes us to a phenomenon that illuminates the very fabric of the nebula's glow: synchrotron radiation, where charged particles dance around magnetic fields in a dazzling display of cosmic energy. Now, let's shine a light on one of the most visually stunning processes that gives the Crab Nebula its ethereal glow: synchrotron radiation. Imagine tiny charged particles like electrons caught in an intricate dance, spiraling around invisible magnetic fields at speeds close to that of light. This cosmic ballet generates some of the most intense radiation we observe in the universe, and it plays a key role in painting the nebula's radiant hues. But what exactly is synchrotron radiation, and why does it matter? To put it simply, when these high-speed particles are deflected by magnetic forces, they release energy in the form of electromagnetic waves. In the case of the Crab Nebula, this radiation spans a wide spectrum from radio waves to X-rays, giving scientists a treasure trove of information about the environment within the nebula. The magnetic fields here aren't just passive players. They actively shape and guide this process, influencing how and where the radiation is emitted. This makes synchrotron radiation an invaluable tool for studying the strength and structure of cosmic magnetic fields, not just in the Crab Nebula but across the universe. Interestingly, the particles responsible for this radiation don't start their journey at such extreme speeds. They're accelerated by powerful forces within the nebula, such as shock waves from the pulsar or turbulent plasma interactions. Once they're moving fast enough, their interaction with magnetic fields creates the dazzling display we detect from Earth. What's even more fascinating is how this phenomenon helps us understand other cosmic environments. By analyzing the synchrotron radiation from the Crab Nebula, researchers can test theories about particle acceleration and refine models that apply to everything from black holes to distant galaxies. And yet, despite its beauty and scientific importance, synchrotron radiation is just one piece of the Crab Nebula's grand puzzle. As we peel back its layers, we uncover yet another remarkable feature: its intricate filamentary structure, a web of gas and dust that offers even more clues about the nebula's turbulent past and dynamic present. Now, let's shift our gaze to one of the Crab Nebula's most defining features: its intricate filamentary structure. These delicate threads of gas and dust stretch across the nebula like a cosmic spiderweb, creating a breathtaking tapestry that tells the story of its explosive origins. But what exactly are these filaments made of, and how did they come to be? At their core, these filaments consist of ionized gas, primarily hydrogen and helium, mixed with heavier elements forged in the heart of the star that once lived here. These elements were violently ejected during the supernova explosion, scattering debris across space. Over time, the intense energy from the pulsar at the center of the nebula has shaped and sculpted this material into the fine, thread-like structures we see today. What's truly fascinating is how these filaments reveal the processes that govern stellar remnants. They act as frozen snapshots of the moment the star met its cataclysmic end, preserving the chemical fingerprints of its interior. By studying their composition, scientists can uncover clues about the star's mass, age, and even the conditions in its final moments. But the filaments are not just static remnants, they are dynamic structures shaped by powerful forces. Shock waves from the pulsar, combined with magnetic fields, compress and heat the gas, causing it to glow in vivid colors. These interactions create a constantly evolving environment where new patterns and formations emerge. And while these filaments may seem delicate, they are anything but fragile. They endure intense radiation and high-energy particle bombardments, offering a glimpse into the resilience of matter in extreme conditions. This intricate interplay of physics not only helps us understand the Crab Nebula, but also provides a template for studying other supernova remnants across the cosmos. As we marvel at the beauty of these filaments, we're reminded that they are more than just a pretty sight. They are a key to unlocking the mysteries of stellar life cycles. And speaking of life cycles, our next phenomenon takes us deeper into the heart of the nebula, where particles are accelerated to mind-boggling speeds, raising questions about the forces that drive this incredible acceleration. Now that we've explored the delicate beauty of the filaments, let's zoom in on one of the most electrifying aspects of the Crab Nebula: how electrons within it are propelled to speeds so close to the speed of light that they defy everyday comprehension. This phenomenon lies at the heart of the nebula's energy engine, but the exact mechanisms driving this acceleration remain shrouded in mystery. Two leading theories have emerged, each proposing a different cosmic culprit. The first suggests that shock waves generated by the pulsar's powerful outflows act as particle accelerators, boosting electrons to their blistering velocities. These shock waves occur when high-speed material crashes into slower-moving gas clouds, creating intense regions of compression and heating. The second theory points to magnetic reconnection, a process where tangled magnetic field lines snap and realign, releasing enormous amounts of energy in the process. This energy could propel electrons to extreme speeds, much like a slingshot hurling them forward. Both mechanisms seem plausible, but which one dominates remains an open question. What we do know is that these accelerated electrons play a crucial role in shaping the nebula's glow. When these near-light-speed electrons spiral around magnetic fields, they emit a type of radiation called synchrotron radiation, responsible for the nebula's dazzling light show across multiple wavelengths. Understanding which process shockwaves or magnetic reconnection takes the lead could unlock deeper insights into the physics of cosmic particle acceleration. And as scientists continue to study this phenomenon, it not only helps us decode the secrets of the Crab Nebula, but also improves our understanding of how similar processes might operate in other extreme environments throughout the universe. With this newfound appreciation for the hidden forces at work, we're ready to explore yet another bizarre feature of the nebula, a phenomenon that reveals its explosive variability in a completely different light. Stepping into another layer of the Crab Nebula's dynamic behavior, we encounter a phenomenon that truly tests the limits of our understanding, its rapid X-ray variability. This peculiar trait refers to sudden and dramatic changes in the intensity of X-rays emitted by the nebula, sometimes occurring in a matter of mere seconds. To put this in perspective, imagine sitting under a flickering light that dims and brightens unpredictably within the blink of an eye. Now picture this happening on a cosmic scale, where the energy involved is billions of times more powerful than anything we experience on Earth. Scientists have long been captivated by these rapid fluctuations because they suggest something incredibly energetic and chaotic is at play deep within the nebula. But what could possibly cause such extreme variability? One leading idea points to the central pulsar itself. This rapidly spinning neutron star acts like a cosmic lighthouse, emitting beams of radiation that sweep across space. However, the pulsar's environment is far from static. The intense magnetic fields surrounding it can twist and snap, releasing bursts of energy that we detect as spikes in X-ray emissions. Another possibility involves the turbulent interactions between the pulsar's wind and the surrounding nebula. When high-speed particles collide with slower-moving material, they create shock fronts that can momentarily amplify X-ray output before fading away. What makes this variability so valuable to scientists is that it provides a window into the most extreme physical conditions imaginable. Temperatures soar to levels that dwarf even the hottest stars, while magnetic fields reach strengths that could shred ordinary matter apart in an instant. By studying these X-ray surges, researchers gain insights into how particles behave under such intense forces, shedding light on processes that might also occur in other high-energy environments like black holes or distant quasars. As we piece together the puzzle of the Crab Nebula's X-ray variability, we're reminded that this celestial wonder isn't just a static relic of a stellar explosion. It's a living, breathing laboratory of cosmic extremes. And speaking of extremes, there's another fascinating feature waiting to be uncovered. One that shifts our focus from invisible wavelengths to something we can almost touch, the surprising presence of dust grains scattered throughout the nebula. Now, let's turn our attention to something unexpectedly delicate amidst the cosmic chaos, the presence of dust grains within the Crab Nebula. If you think about it, dust might not sound all that exciting at first, but when you consider that this dust exists in one of the harshest environments imaginable, its survival becomes nothing short of extraordinary. These aren't the kind of dust particles you'd find floating in your home. These are microscopic grains primarily made of silicates and carbon compounds, forged in the aftermath of the supernova explosion that created the nebula. But how do they form, and more importantly, how do they endure in such an intense and energetic setting? To understand this, we first need to look at the conditions within the nebula. Temperatures here can reach into the millions of degrees, and the radiation bombardment is relentless. Yet somehow, these tiny grains manage to form and persist. Scientists believe the key lies in their formation process, which likely occurs in the cooler, denser regions of the nebula. As material from the exploded star expands outward, it cools enough in certain areas for atoms like silicon, oxygen, and carbon to stick together, forming the building blocks of these dust grains. Think of it like trying to build a snowball in a raging blizzard. It's tricky, but if you find the right spot, it's possible. Once formed, these grains face another challenge: survival. The intense radiation and fast-moving particles within the nebula could easily destroy them. However, researchers have found evidence that suggests the grains might be shielded by larger pockets of gas or denser clumps of material, acting like a protective barrier against the destructive forces around them. Additionally, the size of the grains plays a role. Larger grains are more likely to withstand the harsh conditions compared to smaller ones, which are more vulnerable to being vaporized. But why does this matter? Dust might seem insignificant on a cosmic scale, but it plays a critical role in the universe. These grains can act as seeds for new stars and planets, helping to form the building blocks of future solar systems. In the case of the Crab Nebula, the presence of dust suggests that even in the aftermath of a catastrophic event like a supernova, the ingredients for creation are still present. Some of this dust could eventually drift into neighboring regions of space, influencing the formation of new celestial bodies. What's equally fascinating is what these dust grains tell us about the history of the nebula itself. By studying their composition and distribution, scientists can piece together details about the original star that exploded and how the nebula has evolved over time. For example, the specific types of elements found in the dust grains can reveal information about the star's composition before it went supernova. This makes the dust not just a feature of the nebula, but a kind of time capsule, preserving clues about the past in a way that other phenomena can't. As we transition from the microscopic world of dust grains to the more energetic and dynamic features of the Crab Nebula, we're reminded of the intricate balance between destruction and creation in space. It's a theme that echoes throughout the universe, and as we move forward, we'll see how this balance continues to shape the nebula's behavior in ways both subtle and spectacular. Next, we'll explore how the nebula communicates its secrets through another intriguing phenomenon: its radio wave emissions. Shifting our focus from the tiny yet resilient dust grains, we now turn to a phenomenon that spans vast distances and carries whispers of the Crab Nebula's magnetic heart: its radio wave emissions. These emissions may not be visible to the naked eye, but they hold a treasure trove of information about the nebula's structure and the forces shaping it. To understand why radio waves are so crucial, we need to first grasp what they are and how they emerge from this chaotic cosmic region. Radio waves are a type of electromagnetic radiation, much like visible light but with much longer wavelengths. In the case of the Crab Nebula, these waves are generated by charged particles spiraling around magnetic fields at incredibly high speeds, a process known as synchrotron radiation. This is the same mechanism that gives the nebula its ethereal glow in other wavelengths. But radio waves offer a unique perspective because they can penetrate dense clouds of gas and dust that block other forms of light. This makes them an invaluable tool for astronomers trying to map the nebula's hidden structures. What's truly fascinating is the intricate patterns these radio waves form. When scientists study the Crab Nebula using radio telescopes, they detect a complex web of emissions that trace the nebula's magnetic field lines. These patterns reveal how the magnetic fields twist, stretch, and even reverse direction in some areas. By analyzing these radio wave maps, researchers can infer the strength and orientation of the magnetic fields throughout the nebula. This is critical because magnetic fields play a key role in shaping the nebula's dynamics, influencing everything from particle acceleration to the formation of its iconic jets. But the story doesn't stop there. The Crab Nebula's radio emissions also provide clues about the sources of its energy. Much of the radiation originates near the pulsar at the nebula's core, where high-speed winds of charged particles crash into surrounding material. These collisions not only amplify the magnetic fields but also generate the radio waves we detect from Earth. Additionally, the nebula's outer regions contribute to the emissions, particularly areas where shock waves from the supernova explosion continue to interact with the interstellar medium. This combination of central activity and outer turbulence creates a dynamic symphony of radio signals that change over time. Beyond their role in understanding the Crab Nebula itself, these radio waves have a broader significance. They help astronomers map magnetic fields not just within the nebula but also in the surrounding space. Magnetic fields are invisible yet powerful forces that influence the behavior of galaxies, star-forming regions, and even cosmic rays. By studying the radio emissions from objects like the Crab Nebula, scientists can piece together a larger picture of how magnetic fields shape the universe. It's like using the nebula as a natural laboratory to test theories about the cosmos. As we move deeper into the mysteries of the Crab Nebula, the role of these radio waves becomes even more intriguing. They're not just passive indicators of what's happening within the nebula. They actively shape our understanding of its past, present, and future. With this foundation laid, we're now ready to explore yet another layer of this cosmic enigma, its unusual spectral features in visible light. What secrets might these colors and patterns reveal about the forces at play? Let's find out. Peering into the visible spectrum reveals yet another layer of intrigue within the Crab Nebula, its optical spectra anomalies. These peculiar patterns in visible light are not just beautiful to observe, but also hold clues that baffle even the most seasoned astrophysicists. When astronomers split the light from the nebula into its component colors, they uncover features that defy easy explanation. These anomalies manifest as unexpected shifts, intensities, or even missing lines in the spectrum that don't align neatly with our current understanding of how elements behave under extreme conditions. One of the most striking aspects of these spectral oddities is the presence of emission lines that seem to flicker or vary over time. For instance, the nebula's hydrogen and oxygen emissions, which usually glow steadily in predictable patterns, occasionally exhibit sudden changes in brightness or structure. What could be causing this? One hypothesis suggests that these fluctuations might stem from the pulsar's high-energy winds interacting with the surrounding gas. The winds could strip electrons from atoms in erratic bursts, temporarily altering the light they emit. Another possibility is that magnetic fields within the nebula are distorting the paths of charged particles, creating uneven energy distributions that show up as irregularities in the visible spectrum. Delving deeper, these anomalies also challenge the standard models used to describe plasma behavior in space. For example, some spectral lines appear broader or narrower than expected, hinting at temperatures or densities that don't match theoretical predictions. Could this be evidence of unknown physical processes at work? Scientists speculate that shock waves, turbulence, or even previously unrecognized chemical reactions might be influencing the nebula's optical signature. These findings force researchers to revisit the assumptions baked into their models and adapt them to this ever-surprising cosmic laboratory. What makes these anomalies particularly compelling is how they connect to the broader mystery of the Crab Nebula's origins. The spectral features we observe today are echoes of the cataclysmic supernova explosion nearly 1,000 years ago. By studying them, we're essentially reading the fingerprints of that ancient event, piecing together how the explosion's energy transformed into the dynamic structure we see now. But the more we learn, the more questions emerge. Why do some spectral lines behave so unpredictably? What hidden mechanisms are driving these changes? As we continue unraveling the story of the Crab Nebula, these optical spectra anomalies remind us that even the most dazzling sights in the universe carry secrets waiting to be decoded. And speaking of hidden forces, our journey now takes us to the twisted magnetic fields that shape this cosmic marvel, offering yet another glimpse into the interplay of energy and matter in this extraordinary region. Now, let's shift our focus to a truly fascinating phenomenon: twisted magnetic fields within the Crab Nebula. Imagine invisible forces spiraling and contorting, shaping the environment in ways we're only beginning to understand. These magnetic distortions, often referred to as magnetic field twisting, play a pivotal role in the nebula's behavior, influencing everything from energy flow to the acceleration of particles. What exactly do we mean by twisted magnetic fields? Picture the magnetic field lines that permeate the nebula as threads in a cosmic fabric. Under normal circumstances, these threads might align neatly, creating a predictable pattern. However, in the chaotic heart of the Crab Nebula, these lines twist and coil like tangled wires, creating regions of intense magnetic stress. This twisting is believed to be driven by the rapid rotation of the central pulsar, whose immense magnetic field drags and deforms the surrounding space. These distortions have profound effects on the distribution of energy. For instance, twisted magnetic fields can channel high-energy particles into concentrated streams, amplifying their speed and intensity. This process might explain why we observe such powerful emissions from the nebula, particularly in areas where the magnetic field is most contorted. Think of it like squeezing a hose. When you pinch one end, water bursts out with greater force. Similarly, the twisted fields act as conduits, funneling energy and particles into explosive displays of radiation. Particle acceleration is another area where twisted fields leave their mark. In simpler terms, these spiraling magnetic lines act like cosmic slingshots, flinging charged particles to velocities near the speed of light. This acceleration not only fuels the nebula's luminous glow, but also contributes to the production of high-energy photons and cosmic rays. It's as if the twisted fields are orchestrating a grand symphony of motion, with particles dancing to their magnetic tune. But the story doesn't end there. These magnetic distortions also create zones of instability where particles behave unpredictably. In some regions, the twisting might cause sudden energy releases, akin to miniature explosions, while in others, it could lead to the formation of dense knots of material. Scientists are particularly intrigued by how these processes interact with other phenomena in the nebula, such as shock waves and plasma turbulence. Together, they form a complex web of activity that continues to challenge our understanding of astrophysical processes. The presence of twisted magnetic fields also raises questions about the pulsar's influence over its surroundings. How does the pulsar's spin-down energy translate into the magnetic chaos we observe? Are there other forces at play, such as external pressures from nearby interstellar gas? These questions offer a tantalizing glimpse into the dynamic forces shaping this cosmic laboratory. As we uncover more about these twisted fields, we gain not only insights into the Crab Nebula, but also a deeper appreciation for the fundamental forces that govern our universe. And with that thought, let's now turn our attention to another captivating phenomenon: the wobbling motion of jets emanating from the pulsar, where physics takes yet another surprising turn. As we venture further into the heart of the Crab Nebula, another extraordinary phenomenon captures our attention: the wobbling motion of jets streaming out from the pulsar. Often described as jet precession, this behavior presents yet another cosmic puzzle that continues to intrigue astronomers. To put it simply, these jets don't shoot out in a straight, unwavering path. Instead, they appear to wobble or sway, much like the spinning nozzle of a sprinkler casting water in shifting arcs. So what causes this peculiar motion? One leading explanation points to a process known as precession. In this case, precession refers to the gradual wobble in the rotational axis of the pulsar. Imagine a spinning top as it begins to slow down. Its axis doesn't stay fixed, but instead traces a small circle in the air. Similarly, the pulsar's rapid spin, combined with its intense magnetic field, could cause its jets to trace out a circular or conical pattern over time. This motion might be influenced by the pulsar's interaction with surrounding materials, or even the gravitational pull of a potential companion object. though the latter remains speculative. The implications of this wobbling are far-reaching. For starters, it affects how the jets interact with the nebula's environment. When these high-speed streams of particles shift their orientation, they can carve out new pathways through the surrounding gas and dust, redistributing energy and matter across the nebula. It's akin to a gardener spraying water over a patch of soil, but instead of staying in one direction, the spray pivots, covering a wider area. This dynamic process helps explain some of the unusual structures we observe within the nebula, including regions of heightened activity or peculiar filament formations. But jet precession isn't just about shaping the nebula's interior. It also plays a key role in aligning or misaligning the jets themselves. When the pulsar's axis wobbles, the jets can tilt slightly, altering their trajectory and potentially influencing how energy is channeled into the surrounding space. This variability adds another layer of complexity to the nebula's behavior, making it a living laboratory for studying extreme physics. Interestingly, this phenomenon also raises broader questions about pulsar dynamics. Could the wobbling motion be a result of instabilities within the pulsar's magnetic field, or does it stem from interactions with the nebula's turbulent plasma? Each possibility opens up new avenues for research and invites us to rethink our understanding of these stellar remnants. As we continue to decode the mysteries of jet precession, it becomes clear that this wobbling motion is far more than a mere curiosity. It offers invaluable insights into the forces that govern pulsar behavior and the intricate interplay between rotation, magnetism, and energy. Now, with this fascinating glimpse into the pulsar's jet dynamics, let's turn our focus to an even more extreme aspect of the Crab Nebula, the presence of ultra-high-energy particles that push the boundaries of what we thought was possible. Now that we've explored the wobbling jets and their dynamic influence on the Crab Nebula, let's shift our gaze to something even more extreme: particles so energetic they defy easy explanation. Within this cosmic wonder, ultra-high-energy particles hurtle through space at speeds close to that of light, carrying energies far beyond what we can replicate in laboratories here on Earth. These particles are not just fascinating anomalies, they hold the key to understanding some of the universe's most powerful processes. So where do these ultra-high-energy particles come from? One leading hypothesis points to the pulsar at the heart of the nebula. As it spins furiously, it generates incredibly strong magnetic fields. These fields act like particle accelerators, boosting electrons and other charged particles to almost unimaginable speeds. Imagine a cosmic version of a theme park ride, where particles are whipped around at breakneck speeds, gaining energy with every loop. This process is so efficient that the particles can reach energies millions of times greater than anything we've achieved in machines like the Large Hadron Collider. But the story doesn't stop there. These ultra-high-energy particles also play a crucial role in the production of cosmic rays, streams of high-energy particles that constantly bombard Earth from outer space. The Crab Nebula is believed to be one of the sources of these cosmic rays, ejecting particles into the interstellar medium with such force that they travel vast distances across the galaxy. It's a bit like a cosmic storm where the winds of particles surge outward, spreading energy and matter far beyond the nebula's boundaries. However, there's still much we don't understand about these particles. For instance, how exactly do they achieve such staggering energies? While magnetic fields provide part of the answer, other factors likely come into play. One possibility involves shock waves generated by the pulsar's jets. When these shock waves collide with surrounding material, they could transfer even more energy to the particles, pushing them to ultra-high energy levels. Another idea suggests that turbulence within the nebula's plasma might contribute, stirring up the particles and amplifying their energy through repeated interactions. The presence of these ultra-high energy particles also challenges our understanding of physics. They seem to defy the limits of what's possible based on current models, forcing scientists to explore new theories and refine existing ones. What's more, studying these particles provides a unique window into the conditions of extreme environments, places where gravity, magnetism, and energy combine in ways we're only beginning to comprehend. As we peel back the layers of this phenomenon, it becomes clear that ultra-high-energy particles are more than just a curiosity of the Crab Nebula. They are vital players in shaping the larger cosmic theater, influencing everything from the behavior of nearby space to the fundamental forces that govern the universe. With this mind-bending exploration of ultra-high-energy particles, we're now ready to uncover yet another bizarre mystery: how dust grains manage to survive in one of the most hostile environments imaginable. With the mystery of ultra-high-energy particles still lingering in our minds, let's turn our attention to another cornerstone of the Crab Nebula's enigmatic behavior: its overwhelming dominance of non-thermal radiation. Unlike the light emitted by stars, which is primarily thermal and tied to their heat, the radiation in the Crab Nebula tells a very different story. Here, the energy we detect doesn't come from warmth but from highly energetic processes fueled by magnetic fields and particle acceleration. This non-thermal emission dominates the nebula's glow, painting a picture of a place where physics behaves in ways far removed from the familiar. Non-thermal radiation occurs when charged particles, like electrons, are accelerated to incredible speeds and forced to spiral around magnetic field lines. As they do so, they release radiation across a broad spectrum: radio waves, X-rays, and even gamma rays. This process, known as synchrotron radiation, is the engine behind much of the light we see coming from the Crab Nebula. It's a stark contrast to thermal radiation, which is emitted by objects simply because they're hot. Think of thermal radiation as the gentle glow of a warm fireplace, while non-thermal radiation is like the intense flash of a lightning bolt: wild, unpredictable, and incredibly powerful. What makes non-thermal radiation so crucial in astrophysics is its ability to reveal the hidden dynamics of cosmic environments. In the case of the Crab Nebula, this radiation provides direct evidence of the intense magnetic fields and particle acceleration driven by the central pulsar. Without this non-thermal component, the nebula would look vastly different and far less energetic. In fact, many of the bizarre phenomena we've discussed so far, like the superluminal motion of jets or the gamma-ray flares, owe their existence to these non-thermal processes. To better grasp why this matters, let's consider an analogy. Imagine a bustling city at night, illuminated not by the warm glow of street lamps but by the dazzling lights of neon signs and moving spotlights. These artificial lights aren't powered by heat but by electricity, just as the non-thermal radiation in the Crab Nebula isn't powered by temperature but by magnetic forces and particle dynamics. This distinction helps scientists understand not only the Crab Nebula but also other extreme environments in the universe, like black holes and supernova remnants, where non-thermal processes dominate. Another fascinating aspect of non-thermal radiation is its role in mapping the universe. Because it spans such a wide range of wavelengths, astronomers can study the Crab Nebula using different types of telescopes, from radio to gamma-ray observatories. This multi-wavelength approach has been crucial in piecing together the nebula's complex behavior. For instance, the radio waves reveal the structure of its magnetic fields, while gamma rays highlight the most energetic regions. Together, they give us a comprehensive view of this cosmic powerhouse, but the dominance of non-thermal radiation also raises important questions. Why does it overshadow thermal processes in the nebula? One reason is the sheer energy of the central pulsar, which injects vast amounts of power into its surroundings. This energy fuels the acceleration of particles and the amplification of magnetic fields, creating the perfect conditions for non-thermal emission to thrive. Yet, scientists are still working to fully understand the interplay between these processes and how they shape the nebula's evolution over time. As we marvel at the intricate dance of particles and magnetic fields that produces this non-thermal glow, we're reminded of just how much the Crab Nebula has to teach us about the universe's most extreme environments. But the story doesn't end here. The nebula holds yet another secret, one that might seem impossible at first glance: dense knots of emission scattered throughout its structure, defying expectations and challenging our understanding of how matter behaves in such a chaotic setting. Shifting our gaze to one of the more puzzling features of the Crab Nebula, we find ourselves drawn to the dense knots scattered throughout its glowing expanse. These knots, though small in size compared to the vastness of the nebula, pack a surprising amount of energy and complexity into their structures. They're not just random clumps of material. They're intricate formations that hold clues about the pulsar wind and the nebula's dynamic evolution. To understand these knots, we first need to consider their origin. They likely form as a result of the pulsar wind slamming into the surrounding material of the nebula. This wind, charged with particles moving at near light speeds, creates shock waves that compress gas and dust into dense regions. Over time, these regions evolve, forming knots that can persist for thousands of years. It's almost like watching storm clouds gather and condense, except on a cosmic scale, with forces far beyond anything we experience on Earth. What makes these knots particularly fascinating is their connection to the pulsar wind. The wind itself is a chaotic torrent of energy filled with magnetic fields and high-speed particles. When it interacts with the nebula's slower-moving gas, it creates turbulence that shapes the knots. This process is somewhat analogous to what happens when you pour a fast-moving stream of water into a calm pool. The water doesn't just blend smoothly, it swirls, creating eddies and pockets of concentrated motion. Similarly, the pulsar wind generates areas of higher density where knots can form and thrive. But these knots aren't static, they're constantly evolving. Some knots appear to brighten and dim over time, hinting at internal processes we're only beginning to understand. For instance, they might flare up when fresh material is swept in by the pulsar wind, or they could fade as their energy dissipates into the surrounding environment. This variability makes them invaluable for studying how energy moves through the nebula and how different regions respond to the relentless influence of the pulsar. Interestingly, these dense knots also challenge our understanding of how matter behaves under extreme conditions. In a chaotic environment like the Crab Nebula, where magnetic fields twist and particles accelerate to unimaginable speeds, it's surprising that any structure can hold together at all. Yet, these knots remain stubbornly intact, defying the odds. Scientists believe this resilience might be due to a combination of factors, such as strong magnetic fields acting as a kind of scaffolding, or the knot's own internal dynamics helping them maintain stability. The study of these knots has broader implications too. They serve as miniature laboratories where researchers can test theories about particle acceleration, magnetic field interactions, and the physics of shock waves. In a way, each knot is like a tiny puzzle piece, contributing to the larger picture of how the Crab Nebula and other similar systems operates. By piecing together these clues, we gain insights not just into this single nebula, but into the fundamental forces that shape the universe. As we wrap up our exploration of these dense knots, it's hard not to feel a sense of wonder at their resilience and complexity. They're a testament to the intricate interplay of forces that govern the Crab Nebula. But there's still more to uncover. Up next, we'll delve into another striking feature of this cosmic marvel: the relativistic jets that shoot out from the pulsar, traveling at incredible speeds and shaping the surrounding space in ways that continue to astonish scientists. Now let's zoom in on one of the most electrifying aspects of the Crab Nebula: its relativistic jets. These aren't just ordinary streams of particles, they're cosmic powerhouses shooting out from the pulsar at velocities so extreme they're a fraction of the speed of light. Imagine a fire hose blasting water with such force that it carves through everything in its path. That's essentially what these jets are doing, but on a scale so vast it's almost incomprehensible. The jets are composed of high-energy particles, including electrons and positrons, racing along magnetic field lines that stretch far into space. Their structure is tightly focused, like beams of light from a lighthouse, but instead of sweeping across the sea, these beams pierce through the surrounding nebula. Scientists believe the jets are powered by the intense rotational energy of the pulsar itself, acting as a kind of cosmic engine that converts spin into particle acceleration. What's equally mesmerizing is how these jets interact with their surroundings. As they plow through the nebula, they create shock waves that heat up and compress the surrounding gas. This interaction is like a sculptor shaping clay, carving out intricate patterns and influencing the nebula's overall structure. You can think of it as a cosmic feedback loop. The jets shape the environment, and the environment, in turn, affects the jet's behavior. Their speed is nothing short of astonishing. Traveling at nearly the speed of light, these jets cover distances so vast that even light itself would take years to traverse them. Yet, despite their incredible velocity, they're surprisingly narrow, maintaining their focus over immense stretches of space. This precision raises questions about the mechanisms that keep them so tightly collimated. Could it be the magnetic fields acting as a guide, or is there something else at play that we've yet to fully grasp? Adding to the intrigue is the jet's role in shaping the broader environment of the Crab Nebula. They don't just exist in isolation, they influence the flow of material, the distribution of energy, and even the nebula's overall appearance. For instance, the jets might be responsible for some of the asymmetries observed in the nebula's expansion. It's as if they're leaving a trail of cosmic breadcrumbs, offering clues about the pulsar's activity and the nebula's evolution. Interestingly, these jets also provide a rare opportunity to study physics under extreme conditions. The particles within the jets experience forces and energies far beyond anything we can replicate on Earth. This makes them a natural laboratory for testing theories about relativity, particle acceleration, and magnetic fields. By observing how these jets behave, scientists can refine their understanding of the fundamental forces that govern the universe. As we marvel at the sheer power and precision of these relativistic jets, it's clear they play a pivotal role in the story of the Crab Nebula. Yet there's still much to uncover. How exactly are they generated? What keeps them stable over such immense distances? These are questions that continue to puzzle researchers. But don't worry, our journey isn't over yet. Up next, we'll explore another mind-bending phenomenon: the creation of electron-positron pairs within the nebula's intense fields, shedding light on the high-energy processes that fuel this cosmic wonder. As we venture further into the heart of the Crab Nebula, we encounter a process that sounds like it's ripped straight from the pages of a science fiction novel: the creation of electron-positron pairs. This isn't just some abstract concept reserved for physicists. It's a phenomenon that's happening right now in the nebula's most chaotic regions, and it's rewriting the rules of how we understand the universe. Picture this: in the immense magnetic and electric fields surrounding the pulsar, conditions are so extreme that they can literally tear apart the fabric of space, giving rise to particles and their antimatter counterparts. These pairs consist of electrons, which we're all familiar with, and positrons, their antimatter twins. Together, they're born out of pure energy through a process called pair production. It's a bit like conjuring matter from light, and it happens because the energy in these fields is so intense that it surpasses the threshold needed to create particles from scratch. Now, why does this matter? Well, electron-positron pairs are more than just exotic byproducts of the nebula's high-energy environment. They're key players in shaping the behavior of the pulsar wind and the overall dynamics of the nebula. Once created, these particles spiral around magnetic field lines at near light speeds, emitting radiation in the form of gamma rays and X-rays. This radiation is what gives the Crab Nebula its dazzling glow, but more importantly, it provides a window into the physics of extreme environments. What's truly fascinating is how this process connects to broader theories in physics. Electron-positron pair creation is a cornerstone of quantum electrodynamics, the branch of science that explains how light and matter interact. But the conditions in the Crab Nebula take this theory to its limits, testing predictions that are nearly impossible to verify in a lab. For instance, when a positron encounters an electron, the two annihilate each other, releasing a burst of energy in the form of gamma rays. This cycle of creation and annihilation is happening on a massive scale within the nebula, offering a natural experiment for scientists to study. The implications of this phenomenon stretch far beyond the Crab Nebula itself. Understanding how these pairs form and behave is crucial for unraveling mysteries like black hole jets, gamma-ray bursts, and even the early universe. Could similar processes have occurred moments after the Big Bang? The answers may lie hidden in the behavior of these tiny particles, dancing in the shadow of a distant pulsar. Of course, there's still much we don't know. How do the magnetic fields in the nebula sustain such high-energy particle creation? And what role do these pairs play in the transfer of energy across the nebula? These questions are like pieces of a cosmic puzzle, slowly coming together as new observations emerge. And speaking of energy, our next stop takes us deeper into the nebula's turbulent heart, where shock waves collide and reshape the environment in ways that defy imagination. Stay tuned to uncover how these collisions drive some of the most dramatic changes within this stellar relic. Now, let's shift our focus to one of the most dynamic processes occurring within the Crab Nebula shock wave interactions. If you've ever wondered how the nebula maintains its ever-changing structure, this is where the answers begin to unfold. Shock waves, powerful surges of energy radiating outward from the pulsar, slam into the surrounding material with incredible force. These collisions are anything but ordinary. They're like cosmic sledgehammers reshaping the environment in real time. When these shock waves crash into the nebula's dense clouds of gas and dust, they compress and heat the material to unimaginable temperatures. Think of it like squeezing a balloon filled with air until it starts to warp and change shape. The difference here is that instead of air, we're dealing with particles moving at speeds close to that of light. This intense compression triggers a cascade of effects, from the ionization of atoms to the acceleration of particles, all of which contribute to the nebula's dazzling display. What makes these interactions even more intriguing is their role in driving turbulence within the nebula. When shock waves collide with dense regions, they don't just stop, they bounce back, creating a chaotic web of energy flow. This turbulence mixes materials, stirs up magnetic fields, and even influences how energy spreads throughout the nebula. It's like a cosmic blender, constantly churning and reorganizing the elements in its wake. These processes are vital for shaping the nebula's filamentary structures, those intricate threads we see glowing brightly against the darkness of space. But the effects of shock wave interactions extend beyond just aesthetics. They also play a critical role in particle acceleration, one of the core mysteries of the Crab Nebula. As shock waves ripple through the nebula, they act like cosmic ramps, boosting particles to near-light speeds. These particles then emit radiation across the electromagnetic spectrum, from radio waves to gamma rays, creating the nebula's signature glow. Scientists believe that studying these interactions can help us understand not only the Crab Nebula, but also other energetic environments in the universe, such as supernova remnants and active galactic nuclei. Interestingly, shock wave interactions also hint at a deeper connection between the nebula's small-scale dynamics and its large-scale structure. For example, the asymmetric expansion of the Crab Nebula, a phenomenon we'll explore in more detail later, might be influenced by the uneven distribution of shock waves. Could these waves be the invisible hands sculpting the nebula's lopsided growth? The evidence suggests they might be, but the full picture is still coming into focus. As captivating as these interactions are, they also leave us with plenty of unanswered questions. How do shock waves maintain their energy over such vast distances? and what determines whether a shock wave will compress or disperse the material it encounters. Each new observation brings us closer to unraveling these mysteries, painting a clearer picture of the forces at work. But for now, let's turn our attention to another layer of complexity within the Crab Nebula, its uneven expansion and the factors driving this peculiar behavior. Now that we've explored the role of shock waves in sculpting the Crab Nebula, let's zoom in on another fascinating layer of its behavior: plasma instabilities. These are like the hidden ripples in an otherwise smooth cosmic sea, subtly yet profoundly shaping the environment within the nebula. Plasma, the electrified gas that fills much of the nebula, isn't as stable as it might seem. In fact, it's a hotbed of dynamic activity, prone to fluctuations that can cascade into dramatic effects. Plasma instabilities arise when the delicate balance between charged particles, magnetic fields, and energy flow gets disrupted. Imagine a calm pond where a single drop of water sends out ripples that grow and interact with each other. Similarly, in the Crab Nebula, small disturbances in the plasma can amplify over time, creating chaotic patterns. These instabilities not only warp the magnetic fields threading through the nebula, but also play a pivotal role in how particles are accelerated to extreme speeds. One of the most striking consequences of plasma instabilities is their impact on magnetic structures. You might recall how twisted magnetic fields were discussed earlier. They're not static. Plasma instabilities can stretch, twist, and even snap these fields, releasing bursts of energy in the process. This energy release often manifests as sudden flares of radiation, some of which we observe as gamma rays or X-rays. These phenomena are not just beautiful to study, they provide clues about the underlying physical processes that govern the nebula's behavior, but the story doesn't end there. Plasma instabilities also influence particle acceleration, a cornerstone of the nebula's high-energy activity. As the instabilities disrupt the smooth flow of plasma, they create regions of intense turbulence. These turbulent zones act like natural particle accelerators, boosting electrons and other particles to velocities close to the speed of light. Once accelerated, these particles spiral along magnetic field lines, emitting radiation that contributes to the nebula's radiant glow. What makes plasma instabilities particularly intriguing is their dual nature. They're both creators and disruptors. On one hand, they generate the conditions necessary for some of the nebula's most spectacular displays. On the other, they can destabilize the very structures they help form. This duality adds a layer of complexity to our understanding of the Crab Nebula, highlighting the intricate interplay of forces at work. It's like watching a cosmic dance where every move influences the next, shaping the stage for future performances. As we continue our journey through the mysteries of the Crab Nebula, keep in mind that plasma instabilities are just one piece of the puzzle. They connect to many other phenomena we've discussed, from shock waves to magnetic field distortions, painting a picture of a system in constant flux. But the more we learn, the more questions arise. Are these instabilities the key to unlocking the nebula's deeper secrets, or are they merely surface-level effects of something far more complex? To find out, we'll need to explore further, starting with the nebula's uneven expansion, a phenomenon that ties directly into the forces driving its dynamic behavior. As we pivot from the chaotic dance of plasma instabilities, let's now turn our attention to a phenomenon that paints an even broader picture of the Crab Nebula's dynamic nature: its asymmetric expansion. This is where the nebula's growth tells a story of imbalance and external influences, offering a glimpse into the forces that shape its evolution on a grand scale. The Crab Nebula isn't expanding uniformly in all directions. Instead, it stretches and spreads at different rates, creating an uneven profile that astronomers have been eager to decode. Imagine blowing up a balloon, but instead of inflating evenly, one side bulges outward faster than the other. This lopsided growth mirrors what we observe in the nebula. So, what could be driving this irregular expansion? Scientists believe that external forces are at play here. One possibility is the role of supernova ejecta, the material violently expelled during the original stellar explosion that birthed the nebula. Some regions of this ejecta might carry more momentum or mass, pushing outward with greater force and causing certain areas of the nebula to expand faster. It's like the aftermath of a cosmic explosion where debris doesn't scatter evenly but instead clusters and surges in specific directions. Another factor could be the interstellar medium, the thin gas and dust that fill the space between stars. As the nebula expands, it plows through this medium, encountering varying densities and pressures. Picture a cloud of smoke spreading through a room, but the air currents in different corners push back with differing strengths. In the case of the Crab Nebula, denser regions of the interstellar medium might act as barriers, slowing down expansion in some areas while allowing freer movement in others. These interactions create a complex interplay of forces that shape the nebula's structure over time. Observations show that the western edge of the Crab Nebula, for instance, appears to be expanding more rapidly than the eastern edge. This difference is subtle but significant, hinting at localized conditions that influence its growth. Could there be a denser patch of interstellar gas pressing against one side? Or perhaps the original supernova explosion was not perfectly symmetrical, imparting uneven energy to the expanding debris. What makes this phenomenon so captivating is how it ties into the larger narrative of the nebula's life cycle. The asymmetries we see today could hold clues to the conditions of the supernova itself, offering insights into the explosive event that set everything in motion nearly 1,000 years ago. It also raises questions about how external forces might shape other nebulae across the universe. Are these asymmetries unique to the Crab Nebula, or are they a common feature in stellar remnants? Understanding the uneven expansion of the Crab Nebula doesn't just satisfy our curiosity, it challenges us to rethink how cosmic structures evolve. Every ripple, every push and pull tells a story of resilience and adaptation in the harsh environment of space. And while we've uncovered much about this phenomenon, many mysteries remain. Could hidden magnetic fields or unseen gravitational influences also be at work? As we dig deeper into these questions, the Crab Nebula continues to remind us that even in the vastness of the universe, no detail is too small to spark wonder. With this intriguing glimpse into the nebula's uneven growth, we now set the stage to explore yet another layer of its complexity, its magnetic field twisting, a phenomenon that adds even more twists and turns to this cosmic tale. Now that we've unraveled the mysteries of the Crab Nebula's asymmetric expansion, let's shine a light on another captivating feature, its polarization patterns. These patterns, hidden within the nebula's glow, act like cosmic breadcrumbs, guiding us toward a deeper understanding of its magnetic fields. When astronomers study the light emitted by the Crab Nebula, they don't just look at its brightness or color. They also examine how the light is polarized, meaning the direction in which its electromagnetic waves vibrate. Imagine wearing a pair of polarized sunglasses that filter out glare from sunlight bouncing off a lake. Similarly, the light from the Crab Nebula carries subtle clues about its environment, especially the magnetic fields that permeate the region. What makes this phenomenon so fascinating is that the polarization of light can reveal the orientation and strength of these magnetic fields. In the case of the Crab Nebula, scientists have observed distinct polarization patterns that suggest the magnetic fields are not uniform or static. Instead, they appear to twist and swirl in intricate ways, much like the eddies and currents in a turbulent river. This twisting behavior points to a dynamic interplay between the nebula's magnetic fields and the high-energy particles racing through its interior. But why does polarization matter? Think of it this way: magnetic fields are invisible to the naked eye, yet they play a crucial role in shaping the universe. By studying polarization patterns, astronomers can essentially see these invisible forces at work. For instance, the degree of polarization, the proportion of light waves aligned in a particular direction, can tell us how organized or chaotic the magnetic fields are. High polarization indicates a well-ordered magnetic field, while lower polarization suggests a more tangled and complex structure. In the Crab Nebula, the polarization patterns reveal a magnetic field that's anything but simple. Some regions show strong alignment, hinting at powerful, coherent fields, while others display scrambled polarization, suggesting areas where magnetic reconnection or turbulence might be occurring. These variations provide critical insights into how energy is distributed and transferred within the nebula. What's even more intriguing is how these patterns tie into the broader story of the Crab Nebula's evolution. The magnetic fields don't just influence the nebula's appearance, they also affect how particles are accelerated and how radiation is emitted. By mapping polarization across the nebula, scientists can piece together a more complete picture of its inner workings, from the central pulsar's influence to the outermost reaches of its expanding shell. As we delve deeper into these polarization patterns, one question keeps coming up. What can they tell us about the nebula's past and future? Are the magnetic fields growing stronger, or are they gradually unraveling over time? The answers to these questions could reshape our understanding of not just the Crab Nebula, but also other similar objects scattered throughout the cosmos. With the hidden language of polarization beginning to unfold before us, let's now shift our focus to another enigmatic aspect of the Crab Nebula, its cosmic ray modulation. This is where the story takes an even more energetic turn, as we explore how this stellar remnant influences the flow of high-energy particles across the galaxy. As we journey further into the heart of the Crab Nebula, our exploration takes an electrifying turn literally. Beyond its twisting magnetic fields and radiant glow lies another marvel, its role in shaping the flow of cosmic rays. These high-energy particles, zipping through space at nearly the speed of light, are far from random wanderers. Instead, their paths and energies are influenced by the nebula's dynamic environment, offering us a glimpse into one of the universe's most energetic processes. Cosmic rays are essentially atomic fragments, protons, nuclei, and electrons stripped of their electrons and propelled by powerful forces across galaxies. But when they encounter the Crab Nebula, something extraordinary happens. The nebula acts like a cosmic filter, altering their flow and tweaking their properties in ways scientists are still working to fully decode. Picture it like a bustling highway where cars representing cosmic rays are forced to slow down, speed up, or even change lanes due to uneven road conditions. Only here, the road conditions are shaped by the nebula's magnetic fields and particle interactions. What makes this phenomenon so compelling is how the Crab Nebula not only affects the quantity of cosmic rays passing through, but also their energy levels. Astronomers have observed fluctuations in both the flux, the number of particles arriving per second, and the energy spectrum, which describes the range of energies these particles carry. These variations are believed to stem from the intense magnetic fields and turbulent plasma within the nebula. For instance, when cosmic rays interact with magnetic fields, they can lose energy through a process called synchrotron radiation, which we've touched on earlier. This energy loss subtly reshapes the cosmic ray population passing through the region. But the story doesn't end there. The nebula isn't just a passive participant in this cosmic dance, it actively modulates the cosmic rays. Think of it as a cosmic blender, mixing and altering the energies of particles as they journey through its chaotic interior. In some regions, the magnetic fields are so strong that they can trap cosmic rays in tight spirals, forcing them to emit radiation before escaping. In other areas, shock waves from the pulsar's activity might give these particles a boost, propelling them to even higher energies. This modulation process is a key reason why the Crab Nebula serves as a natural laboratory for studying cosmic rays, which are notoriously difficult to observe directly on Earth. Understanding these interactions offers more than just academic intrigue. Cosmic rays play a significant role in shaping the universe around us. They can influence the formation of clouds, affect atmospheric chemistry, and even pose risks to space travel. By studying how the Crab Nebula modulates cosmic rays, scientists hope to uncover broader principles governing their behavior across the cosmos. For instance, could similar modulation processes occur in other supernova remnants or active galactic nuclei? The answers could help explain why certain regions of space are teeming with high-energy particles while others remain relatively quiet. This phenomenon also ties back to the central pulsar's immense power. The pulsar's relentless energy output not only drives the nebula's expansion, but also stirs up the magnetic turbulence that influences cosmic rays. It's a reminder of how interconnected the Crab Nebula's features are. Each phenomenon we explore builds upon the last, painting a richer, more intricate picture of this stellar enigma. As we step back from the high-energy interactions within the nebula, it's time to turn our attention inward to the shock waves that ionize surrounding gases and reveal yet another layer of the Crab Nebula's complexity. These ionization shocks, glowing with fierce energy, hold clues to the nebula's past and its role in heating and shaping its surroundings. Let's delve into this fiery phenomenon and uncover how it continues to reshape our understanding of stellar remnants. As we shift our gaze to the fiery edges of the Crab Nebula, we encounter a phenomenon that breathes life into its surroundings: ionization shocks. These powerful waves of energy rip through the surrounding gas, transforming it in ways that are as fascinating as they are vital to the nebula's evolution. Imagine a cosmic broom sweeping through space, not just clearing a path but igniting the very atoms it touches. That's precisely what these shocks do, stripping electrons from gas particles and leaving behind a sea of charged ions that glow with intense energy. The process begins when shock waves, born from the pulsar's relentless activity, collide with the cooler gas that lingers around the nebula. These waves, traveling at supersonic speeds, carry enough energy to heat the gas to millions of degrees. As the gas heats up, its chemical composition begins to change. Atoms that were once neutral become ionized, meaning they lose their electrons and take on new properties. This transformation is crucial because it alters how the gas interacts with its environment, influencing everything from its radiation emissions to its role in forming new structures within the nebula. But the effects of ionization shocks go far beyond just heating the gas. They also play a key role in shaping the nebula's chemical fingerprint. When these shocks pass through, they can break apart molecules and rearrange atoms, creating new chemical compounds in the process. For example, elements like hydrogen and helium, which make up the bulk of the surrounding gas, can be transformed into heavier elements. This not only enriches the nebula's composition, but also contributes to the broader cycle of matter in the universe. It's a reminder that even in destruction, there's creation, a cosmic balancing act that drives the life cycle of stars and galaxies. What makes ionization shocks even more intriguing is their role in revealing the hidden dynamics of the Crab Nebula. These glowing regions, often seen as bright filaments in telescopic images, act like cosmic thermometers. By studying their light, scientists can determine the temperature, density, and motion of the gas, painting a clearer picture of the forces at play. For instance, the intensity of the light emitted by ionized gas can tell us how strong the shock waves are and how much energy they carry. This data helps researchers piece together the puzzle of how the nebula's interior churns and evolves over time. Interestingly, these shocks don't just heat and ionize, they also help maintain the nebula's structure. By compressing gas into dense knots and filaments, they create the intricate web-like patterns we see in images of the Crab Nebula. These dense regions, in turn, become sites where new physical processes unfold, such as the formation of dust grains or the acceleration of particles to near light speeds. It's a dynamic interplay of forces that keeps the nebula alive with activity, long after the supernova that birthed it has faded into memory. As we step back from the fiery chaos of ionization shocks, it's hard not to marvel at how interconnected these phenomena are. Each discovery leads us deeper into the nebula's story, revealing layers of complexity that challenge our understanding of the universe, but the journey doesn't end here. Just ahead, we'll explore the turbulent gas dynamics that keep this stellar remnant in constant motion, adding yet another chapter to the Crab Nebula's ever-unfolding mystery. Moving from the intricate dance of ionization shocks, we now turn our attention to another captivating aspect of the Crab Nebula, its temporal variability. This is where the nebula reveals its knack for keeping astronomers on their toes, as it exhibits sudden and unexpected changes in brightness and structure over surprisingly short periods. Picture this: you're observing the nebula through a telescope, and just when you think you've captured its essence, it flickers, brightens, or subtly shifts its appearance. These fluctuations occur over timescales ranging from mere seconds to weeks, defying easy explanation. Scientists have been able to attribute some of these variations to transient phenomena, such as bursts of energy from the pulsar or sudden flares in high-energy radiation. Yet, many of these changes remain shrouded in mystery, hinting at mechanisms we have yet to fully understand. One of the most intriguing aspects of temporal variability is its unpredictability. For instance, the nebula's X-ray emissions have been observed to spike without warning, sometimes doubling in intensity within a matter of hours. These bursts of activity are believed to be tied to the pulsar's magnetic field, which can channel energy in ways that are still not entirely clear. Similarly, in the optical spectrum, certain regions of the nebula have been seen to brighten and dim sporadically, almost as if the nebula is breathing. What makes this phenomenon even more fascinating is the possibility that we're witnessing the interplay of multiple forces at once. For example, the same shock waves responsible for ionizing gas might also trigger brief but intense flashes of light as they compress and heat surrounding material. Or perhaps the magnetic fields threading through the nebula are rearranging themselves, releasing stored energy in sudden bursts. These are just a few of the theories, but none provide a complete picture. The study of temporal variability also highlights the importance of modern technology in unraveling cosmic mysteries. Instruments like space-based telescopes and high-speed cameras allow researchers to capture these fleeting changes with incredible precision. By analyzing patterns in the data, they can piece together clues about the nebula's inner workings. For instance, the timing and intensity of these fluctuations can reveal details about the pulsar's spin or the density of the surrounding plasma. Yet, despite these advances, temporal variability reminds us that the Crab Nebula still holds secrets that elude even our most sophisticated tools. The short-term changes we observe could be the result of processes occurring deep within the nebula, hidden from direct view. Or they might point to entirely new physics waiting to be discovered. Either way, they underscore the nebula's role as a dynamic and ever-changing laboratory for studying the extremes of the universe. As we continue our journey through the mysteries of the Crab Nebula, let's carry this sense of wonder forward. Up next, we'll delve into the twisted magnetic fields that warp and distort the energy flowing through this stellar remnant, adding another layer of complexity to its already astonishing story. Stepping into another extraordinary feature of the Crab Nebula, we encounter magnetic reconnection events, dramatic moments where the magnetic fields within the nebula undergo sudden and explosive realignments. These events are akin to the universe's own fireworks, releasing vast amounts of stored energy in the blink of an eye and playing a crucial role in shaping the environment around the pulsar. Magnetic reconnection occurs when tangled or oppositely directed magnetic field lines snap and then reconnect, unleashing immense energy in the process. This phenomenon is not unique to the Crab Nebula. It happens throughout the cosmos, but the conditions here make it especially powerful and revealing. Within the nebula, the pulsar's intense magnetic field interacts with surrounding particles and plasma, creating a cauldron of activity where reconnection events can accelerate particles to near light speeds. What's fascinating about these events is their dual role. First, they act as a release valve for pent-up magnetic energy. Imagine stretching a rubber band to its limit and then letting it snap back. The snap represents the magnetic field lines breaking apart and reconnecting. This releases bursts of high-energy radiation, which we detect as flares across various wavelengths, from X-rays to gamma rays. Second, magnetic reconnection serves as a natural particle accelerator. As the field lines rearrange, they fling charged particles like electrons and protons into higher energy states, contributing to the nebula's dazzling emissions and its reputation as a cosmic powerhouse. To better understand this, think of a pinball machine. When the magnetic fields reconnect, particles are like the pinballs, getting launched at incredible speeds and bouncing around in chaotic yet predictable patterns. These high-speed particles interact with the nebula's magnetic fields and emit the synchrotron radiation that gives the Crab Nebula its iconic glow. Without magnetic reconnection, the nebula might appear far dimmer and less dynamic. Interestingly, scientists believe that magnetic reconnection events could also influence the pulsar's jets. These jets, which shoot out from the pulsar's poles at relativistic speeds, seem to draw energy from the same processes that drive reconnection. This connection suggests that the pulsar and its surrounding nebula are deeply intertwined systems, constantly exchanging energy and particles in ways we're only beginning to comprehend. For researchers, studying magnetic reconnection in the Crab Nebula offers more than just insights into this particular stellar remnant. It provides a window into a fundamental astrophysical process that occurs in everything from solar flares on our Sun to distant black hole environments. The Crab Nebula acts as a natural laboratory, allowing astronomers to observe these events up close and in unprecedented detail. As we marvel at the explosive beauty of magnetic reconnection, let's keep our telescopes and our minds open to the mysteries still unfolding. Up next, we'll explore how the production of high-energy photons in the Crab Nebula adds yet another layer to its reputation as one of the most extreme and fascinating regions in space. Now that we've uncovered the explosive role of magnetic reconnection, let's venture into another cornerstone of the Crab Nebula's mystique, the production of high-energy photons. These photons, some of the most energetic particles in the universe, are like cosmic messengers, carrying vital clues about the extreme processes at play within the nebula. High-energy photons are born in the chaotic heart of the nebula, where particles are accelerated to unimaginable speeds. When charged particles, such as electrons, are flung into intense magnetic fields, they spiral around those fields at velocities close to the speed of light. This motion generates radiation known as synchrotron emission, which spans a wide range of wavelengths. But in the case of the Crab Nebula, something even more remarkable happens. When these ultra-fast particles collide with lower-energy photons, they can boost them into the high-energy gamma-ray range through a process called inverse Compton scattering. What makes these photons so fascinating isn't just their origin, it's how scientists detect them and what their presence tells us about particle acceleration. Earth-based observatories and space telescopes equipped with gamma-ray detectors have captured these photons streaming from the Crab Nebula. These observations allow astronomers to study the nebula's inner workings in exquisite detail, revealing the conditions needed to create such energetic emissions. For instance, the detection of gamma rays with energies exceeding 100 billion electron volts has stunned researchers, pushing the boundaries of what we thought possible in particle acceleration. To put this into perspective, think of a roller coaster speeding through twists and turns. The faster the coaster moves, the more thrilling the ride becomes. Similarly, the particles in the Crab Nebula are pushed to their limits, creating a cosmic ride that ends with the emission of these high-energy photons. These photons serve as a window into the nebula's most extreme environments, offering insights into how magnetic fields and shockwaves work together to fuel such intense phenomena. But the implications of high-energy photons stretch beyond just the Crab Nebula. By studying them, researchers can test theories about particle acceleration in other astrophysical settings, such as active galactic nuclei or supernova remnants. These photons help us understand the fundamental physics of how particles gain energy and how radiation is produced in the universe's most violent regions. As we continue to map the nebula's secrets, these high-energy photons remind us of the Crab Nebula's role as a natural laboratory for extreme astrophysics. Yet, even as we unravel these enigmas, new questions arise. What happens when these photons interact with the surrounding interstellar medium? And what can they tell us about the pulsar's role in powering the nebula? These puzzles lead us to our next stop, where we'll explore the turbulent gas dynamics that add another layer of complexity to this cosmic marvel. As we shift our gaze from the high-energy photons, we find ourselves plunging into another remarkable feature of the Crab Nebula, its turbulent gas dynamics. This phenomenon is like the cosmic equivalent of a stormy ocean, where chaos and motion reign supreme. But why does this turbulence matter, and how does it shape the nebula's behavior? Let's take a closer look. Turbulence in the Crab Nebula isn't just random motion. It's a critical process driving how energy moves and materials mix within the nebula. Picture a pot of boiling water with bubbles rising and swirling in unpredictable patterns. Similarly, the gas in the nebula is in constant motion, stirred by shockwaves from the pulsar and the explosive forces of the supernova remnant. These chaotic movements play a key role in spreading energy throughout the nebula, ensuring that no single region remains static. One of the most fascinating aspects of this turbulence is how it contributes to energy dissipation. As gas swirls and collides, some of the kinetic energy from these movements is converted into heat and radiation. This dissipation helps maintain the nebula's glow while also influencing the temperatures and pressures within different regions. For example, areas with more intense turbulence tend to be hotter and brighter, offering visual clues about the underlying physical processes at play. But turbulence doesn't just spread energy, it also mixes materials. The Crab Nebula is a cosmic melting pot, filled with elements forged in the heart of the exploded star. As turbulent gas moves, it carries these elements across vast distances, blending them with surrounding interstellar material. This mixing is vital for understanding how supernova remnants enrich the universe with heavy elements like iron and silicon, which eventually become part of new stars, planets, and even life itself. To study this phenomenon, astronomers rely on advanced simulations and observations from telescopes that capture the nebula in different wavelengths. These tools reveal intricate details about how turbulence sculpts the nebula's structure, showing how smaller eddies and larger flows interact to create a dynamic and ever-changing environment. For instance, some regions of the nebula display filament-like structures that appear to twist and stretch, a direct result of turbulent forces at work. Interestingly, turbulence in the Crab Nebula also serves as a testing ground for theories about how similar processes occur in other astrophysical settings. Whether it's the swirling gases around black holes or the chaotic motion in star-forming regions, turbulence is a universal feature of the cosmos. By studying it in the Crab Nebula, scientists gain valuable insights into how these processes shape the broader universe. As we piece together the puzzle of turbulent gas dynamics, we begin to see how interconnected the nebula's features truly are. From the shockwaves that drive the chaos to the mixing of materials that enriches the cosmos, turbulence is a cornerstone of the Crab Nebula's story. And yet, as we leave this swirling maelstrom behind, we find ourselves drawn to another intriguing aspect, the survival of dust grains in such a seemingly hostile environment. Let's explore how these tiny particles endure and what their presence reveals about the nebula's hidden secrets. Now, let's turn our attention to one of the most surprising elements within the Crab Nebula, dust grains. These tiny particles might seem insignificant compared to the vast energies and chaotic motions we've explored, but their survival in such a harsh environment is nothing short of extraordinary. Dust grains in the Crab Nebula exist in a place that's constantly bombarded by high-energy radiation, shock waves, and intense magnetic fields. To understand how they endure, we need to consider two key factors: shielding effects and grain size distributions. Imagine these grains as cosmic survivors, each with its own strategy for staying intact amidst the chaos. Shielding plays a crucial role in their survival. Larger grains are often able to shield their interiors from the most destructive forces. Think of them like tiny armored vehicles, with their outer layers absorbing the brunt of the damage while protecting the material inside. This shielding allows some grains to maintain their structure even as they're exposed to the relentless energy of the nebula. Grain size also matters significantly. Smaller grains are more vulnerable because they have a larger surface area relative to their volume, making them more susceptible to destruction by high-energy particles and radiation. On the other hand, larger grains are more resilient as their bulk provides better resistance to these destructive forces. Observations suggest that there's a size sweet spot where grains are just large enough to survive but not so large that they're easily disrupted by collisions or other forces. Scientists believe that the distribution of grain sizes in the nebula tells a story about its history. By analyzing the types of grains present, researchers can infer details about the original supernova explosion and the subsequent evolution of the nebula. For instance, certain grains may have formed directly from the ejected material of the dying star, while others might have condensed later as the nebula cooled. But the question remains, why does this matter? Dust grains play a vital role in the universe. They act as the building blocks for stars, planets, and even life itself. By studying how these grains survive in the extreme conditions of the Crab Nebula, scientists gain insights into the life cycle of matter in the cosmos. For example, the presence of dust in environments like this shows how supernova contribute to the enrichment of interstellar space with essential elements. Interestingly, some grains may also find protection in regions of the nebula with lower energy levels or denser gas clouds. These areas act like cosmic shelters, offering a reprieve from the otherwise hostile surroundings. Observations across different wavelengths reveal that these grains emit infrared radiation as they absorb energy and re-radiate it, providing clues about their temperature and composition. As we continue to investigate these resilient particles, we find yet another layer of complexity in the Crab Nebula's story. Dust grains, though small, connect us to the larger processes shaping the universe. And now, with a glimpse into their survival strategies, we're ready to explore the next curious phenomenon: shifts in spectral lines and what they reveal about the motion and dynamics within the nebula. Let's dive in and see what these cosmic fingerprints can tell us about the forces at work in this extraordinary region. Moving forward, let's unravel another fascinating aspect of the Crab Nebula spectral line shifts. These subtle yet significant changes in the light emitted by elements within the nebula serve as cosmic fingerprints, revealing the motion and dynamics at play in this chaotic region. Spectral lines are like the universe's barcodes, each one corresponding to a specific element. When we observe these lines shifting, it's often due to the Doppler effect. Imagine a race car speeding past you. The sound of its engine changes as it approaches and then moves away. Similarly, when particles in the nebula move toward or away from us, the wavelengths of their emitted light stretch or compress, causing these spectral lines to shift. What makes this phenomenon so intriguing is how it helps us map the velocities of materials within the Crab Nebula. For instance, if spectral lines appear shifted toward the blue end of the spectrum, it means the material is moving toward us. Conversely, a redshift indicates movement away from us. By analyzing these shifts across different regions of the nebula, scientists can create a detailed velocity map showing how gas and dust are swirling, colliding, and spreading outward. But the story doesn't stop there. These shifts also highlight the presence of velocity gradients, areas where the speed of material changes over distance. Picture a cosmic whirlpool where particles near the center are moving faster than those further out. These gradients provide clues about the forces shaping the nebula, such as shock waves from the pulsar or interactions with the surrounding interstellar medium. What's truly remarkable is how these observations deepen our understanding of the Crab Nebula's energy distribution. For example, regions with extreme velocity gradients often correspond to sites of intense turbulence or shock interactions. These findings not only help us interpret the nebula's current state, but also piece together its chaotic past. As we analyze these spectral line shifts, we begin to see the Crab Nebula not as a static object, but as a dynamic, ever-evolving system. Each shift tells a story of motion, energy, and transformation, painting a vivid picture of the forces at work. And with that, we're ready to explore the next layer of this cosmic puzzle. What happens when shock waves ionize the surrounding gas, and how does this affect the nebula's structure and composition? Let's find out. Now, let's shift our focus to one of the most intriguing aspects of the Crab Nebula, the cooling rates of its central neutron star. This dense, city-sized remnant of the supernova explosion holds secrets about the universe's most extreme physics, and studying how it cools over time offers clues about its age and internal makeup. Neutron stars are among the densest objects in the universe, with a teaspoon of their material weighing billions of tons. But despite their incredible density, these stars aren't static. They gradually lose heat over thousands of years. The rate at which this cooling occurs can tell us a lot. For the neutron star at the heart of the Crab Nebula, careful observations have revealed a cooling process that aligns with its estimated age of just over 900 years. This agreement between cooling models and historical records of the supernova provides a fascinating cross-check for astrophysical theories. But how exactly does a neutron star cool? There are several mechanisms at play. Initially, the star radiates heat through neutrinos, nearly massless particles that escape its core, carrying away energy. This phase dominates the cooling process for the first few thousand years. Later, the star's surface begins to emit photons, contributing to further heat loss. By comparing these cooling mechanisms to the observed temperature of the Crab Nebula's neutron star, scientists can infer details about its internal structure, such as the composition of its core, whether it's filled with neutrons or even stranger forms of matter like quark soup. What makes this phenomenon so captivating is how it bridges the gap between theory and observation. Models suggest that if the core contains exotic matter, the cooling rate might differ from what we'd expect with a more conventional neutron star. Each new observation brings us closer to answering one of astrophysics' biggest questions: what lies at the heart of these enigmatic objects? As we continue to study the neutron star's cooling rates, we gain not only insights into the Crab Nebula's past, but also a deeper understanding of the fundamental forces shaping the universe. With this knowledge in hand, it's time to turn our attention to another fascinating feature of the nebula: its infrared emission bands, which reveal how heated dust contributes to the energy budget of this cosmic wonder. Let's dive in. Moving forward, let's explore a captivating phenomenon that sheds light, quite literally, on the energetic dynamics of the Crab Nebula. This is the presence of infrared emission bands, a feature that offers profound insights into the role of dust within this cosmic marvel. When we talk about the Crab Nebula, it's easy to picture it as a realm dominated by high-energy processes like gamma rays and X-rays. But there's also a gentler, yet equally important side to this story: heat. Within the nebula, grains of dust are heated by the energetic emissions from the central pulsar and surrounding structures. As these dust grains absorb energy, they re-radiate it in the form of infrared light, creating distinct emission bands that astronomers can detect and study. Why does this matter? These infrared bands are more than just a byproduct of the nebula's activity. They're a key piece of the puzzle when it comes to understanding its energy budget. Think of the nebula as a giant engine with various processes contributing to its overall output. The infrared emissions reveal how much energy is being rerouted into heating dust, offering clues about the balance between high-energy radiation and the thermal processes at play. Interestingly, these dust grains aren't uniformly distributed. They cluster in certain regions, often near the filaments that weave through the nebula. This uneven distribution tells us about the complex interplay between the pulsar wind, magnetic fields, and the surrounding material. It's a delicate dance where energy is transferred, absorbed, and re-emitted in ways that shape the nebula's appearance and behavior. For astronomers, studying these infrared bands isn't just about mapping energy flow. It also helps them understand the life cycle of dust in extreme environments. Dust plays a crucial role in the cosmos, acting as a building block for stars and planets. By examining how dust survives and evolves in the intense conditions of the Crab Nebula, scientists can refine their models of star formation and galactic evolution. So, as we marvel at the intricate patterns of infrared light woven into the fabric of the Crab Nebula, it's worth pausing to appreciate the bigger picture. These emissions are a testament to the dynamic processes that continue to shape this stellar remnant, bridging the gap between the smallest particles and the largest cosmic structures. And with that in mind, let's now turn our attention to another fascinating aspect of the nebula: how electric and magnetic forces combine to influence the motion of particles within its vast expanse. As we shift our gaze to yet another intriguing layer of the Crab Nebula's complexity, we find ourselves diving into the subtle but crucial phenomenon of particle drifts. These drifts might sound like a small detail, but they play a massive role in how particles move and behave within this cosmic powerhouse. To understand particle drifts, we need to talk about the dynamic interplay between electric and magnetic forces. Picture this: within the nebula, charged particles like electrons and ions are constantly on the move. But they're not just zipping around randomly, they're being steered by invisible forces. Magnetic fields act like a cosmic highway, guiding these particles along curved paths. At the same time, electric fields give these particles an additional push, nudging them in specific directions. Together, these forces create a kind of cosmic choreography, shaping the trajectories of particles as they traverse the nebula. What makes this process fascinating is how it influences the bigger picture. For example, particles drifting in specific patterns can reveal the strength and orientation of magnetic fields within the nebula. Scientists study these drifts to map out the magnetic landscape, much like how a hiker might use the flow of a river to understand the terrain. The drifts also affect how energy is distributed throughout the nebula. Some particles gain energy, spiraling faster and faster, while others lose energy, slowing down and settling into lower energy states. Another key aspect of particle drifts is their role in shaping the nebula's emissions. As particles drift through different regions, they interact with varying levels of energy and radiation. These interactions can produce the stunning emissions we observe across the electromagnetic spectrum, from radio waves to X-rays. In fact, some of the most striking features of the Crab Nebula might owe their existence to these subtle drift motions. Interestingly, particle drifts aren't just important for understanding the Crab Nebula, they also serve as a natural laboratory for testing physics. Here on Earth, recreating the extreme conditions found in the nebula is nearly impossible. But by studying how particles behave in this distant cosmic arena, scientists can refine their theories about plasma physics and the fundamental forces that govern the universe. As we continue our journey through the mysteries of the Crab Nebula, it's clear that even the smallest motions can have profound implications. Particle drifts remind us that the universe is a place of intricate balance, where forces we can't see directly shape the grandest of cosmic phenomena. With that in mind, let's now delve into the next piece of the puzzle, the efficiency of shock heating and how it energizes this spectacular stellar remnant. Now, let's peel back another layer of this cosmic marvel as we explore how shock heating breathes energy into the Crab Nebula. Shock heating might sound like a term straight out of a sci-fi movie, but it's actually a fundamental process that helps explain why this stellar remnant shines so brilliantly. To put it simply, shock heating occurs when particles crash into each other at incredibly high speeds, converting their kinetic energy into heat and radiation. This phenomenon acts like an invisible engine fueling much of the nebula's luminous glow. Picture a speeding car suddenly slamming on the brakes. It doesn't just stop. The energy has to go somewhere, often as heat or sound. Similarly, in the Crab Nebula, shock waves rippling through its vast clouds of gas and particles slam into surrounding material. These collisions generate immense heat, raising the temperature of the gas to millions of degrees. This is why we can detect the nebula's emissions not just in visible light, but also in X-rays and other high-energy wavelengths. These shock waves are driven by the powerful pulsar at the nebula's core, which constantly spews out streams of charged particles and magnetic fields. But how efficient is this process? That's where things get even more fascinating. Scientists use a mix of observational data and computer simulations to study the exact mechanisms behind shock heating. From telescopic observations of the nebula's emissions, they can estimate the energy involved in these shocks. Then, by running detailed simulations, they test whether their theoretical models match reality. The results have been remarkable but also puzzling. For instance, observations suggest that shock heating in the Crab Nebula is far more effective at energizing particles than what some models predict. This discrepancy has sparked intense debate and research. Are there hidden factors at play, such as turbulence or magnetic reconnection, that amplify the heating process? These questions highlight why the Crab Nebula remains such a treasure trove for astrophysicists. Every answer seems to unlock even deeper mysteries. For example, understanding shock heating not only helps explain the Crab Nebula's brilliance, but also provides insights into similar processes in other cosmic environments, like supernova remnants and galaxy clusters. By studying how energy flows through this system, scientists can refine their understanding of plasma dynamics and the behavior of matter under extreme conditions. As we move deeper into the heart of the Crab Nebula's secrets, this exploration of shock heating sets the stage for our next revelation: how quickly electrons lose their energy and what that tells us about the nebula's dynamic environment. Now that we've uncovered the role of shock heating in powering the Crab Nebula, let's turn our attention to another critical piece of the puzzle: how electrons shed their energy over time. This phenomenon, known as electron cooling, might not sound as explosive as shock waves, but it's just as vital in shaping the nebula's behavior and appearance. Understanding electron cooling timescales gives us a clearer picture of the dynamic processes at play and helps explain why the nebula looks the way it does across different wavelengths of light. To grasp this, imagine electrons as tiny particles zooming through space at nearly the speed of light, energized by the pulsar's relentless winds and magnetic fields. But these electrons don't stay supercharged forever. Over time, they lose their energy through various mechanisms, and the rate at which this happens is what scientists call the cooling timescale. One of the primary ways electrons cool down is by emitting radiation. Depending on their energy levels, they can produce different types of light, from radio waves to X-rays and gamma rays. This radiation not only paints the nebula's stunning glow, but also gives astronomers clues about the electron's journey. There are several key mechanisms driving electron cooling in the Crab Nebula. Synchrotron radiation is one of the most important. This occurs when high-energy electrons spiral around magnetic field lines, emitting photons in the process. The stronger the magnetic field, the faster the electrons lose energy. Another process is inverse Compton scattering, where electrons collide with low-energy photons, like those from the cosmic microwave background, and boost them to much higher energies. Both of these mechanisms contribute to the nebula's multi-wavelength emissions, but they also drain the electron's energy at different rates. What's fascinating is how these cooling timescales vary depending on the electron's initial energy. Higher energy electrons cool much faster than their lower energy counterparts, sometimes losing most of their energy in just a few months or years. On the other hand, lower energy electrons can linger for thousands of years, slowly radiating away their remaining energy. This difference creates a complex interplay of emissions that evolves over time, giving the Crab Nebula its ever-changing appearance when viewed through telescopes. By studying these cooling timescales, researchers can piece together the nebula's history and predict its future. For instance, if electrons cool too quickly, it could mean the magnetic fields are stronger than expected, or that the pulsar's energy output is fluctuating. These insights aren't just limited to the Crab Nebula, they also apply to other cosmic environments, like active galactic nuclei and gamma-ray bursts. As we dig deeper into this phenomenon, it becomes clear that the Crab Nebula is not just a relic of a stellar explosion, but a living laboratory where the universe's most extreme processes unfold before our eyes. With this understanding of electron cooling in mind, we're now ready to tackle an even stranger mystery: the unexpected shifts in dispersion measures that hint at the nebula's ever-changing plasma environment. As we shift our focus to yet another cosmic oddity, let's explore the intriguing phenomenon of anomalous dispersion measures within the Crab Nebula. These deviations are more than just random fluctuations. They are clues that hint at the ever-changing density of plasma throughout this dynamic region. To unravel this mystery, picture the nebula as a vast, glowing cloud filled with charged particles. When signals from the pulsar travel through this turbulent environment, they encounter varying densities of plasma, causing the light to spread out or disperse. These dispersion measures act like a cosmic fingerprint, revealing how the plasma is distributed and how it shifts over time. What makes these anomalies so captivating is their unpredictability. Scientists have observed that the dispersion measures don't remain constant, they waver, sometimes dramatically, over short periods. This suggests that the plasma density within the nebula isn't uniform or stable. Instead, it's a chaotic sea of charged particles, constantly stirred by the pulsar's energetic winds and magnetic fields. These fluctuations challenge our understanding of how such environments evolve, forcing researchers to reconsider the forces at play. One possible explanation for these deviations lies in the interaction between the pulsar's wind and the surrounding nebula material. When the high-speed wind collides with denser regions of plasma, it can compress or displace them, leading to localized changes in dispersion. Another factor could be the presence of shock waves, which we've already touched on, rippling through the nebula and temporarily altering the plasma's density. Together, these processes create a complex tapestry of dispersion patterns that astronomers are only beginning to decode. The implications of these findings extend far beyond the Crab Nebula itself. By studying how plasma behaves in such an extreme environment, scientists can refine their models of other astrophysical phenomena like fast radio bursts and distant quasars. This makes the Crab Nebula not just a subject of intrigue, but also a key testing ground for broader cosmic theories. As we continue piecing together the puzzle of anomalous dispersion measures, we're reminded once again of how this celestial wonder serves as both a relic of the past and a laboratory of the future. With this deeper understanding of plasma density shifts, it's time to delve into the fascinating world of magnetic towers structures that may hold the key to unlocking even more secrets hidden within the heart of the nebula. Now, let's turn our attention to a fascinating concept that could reshape how we understand the architecture of the Crab Nebula: magnetic tower models. These theoretical frameworks propose that towering structures of magnetic fields may be responsible for shaping and stabilizing the nebula's intricate framework. Imagine these magnetic towers as colossal, invisible scaffolds, extending outward from the pulsar and influencing the surrounding environment in profound ways. They are thought to channel energy and particles into specific directions, sculpting the nebula's glowing filaments and defining its dynamic structure. What makes magnetic tower models so compelling is their ability to explain some of the nebula's most perplexing features. For instance, researchers have long puzzled over how the Crab Nebula maintains its highly organized jets and the overall symmetry of its emissions. Magnetic towers could provide an answer. According to these models, the intense magnetic fields generated by the pulsar at the nebula's core twist and stretch as they expand outward. This twisting action creates a helical structure, much like the shape of a coiled spring, that helps to collimate or focus the high-speed jets we observe shooting out from the pulsar. These jets, in turn, play a critical role in shaping the surrounding gas and plasma, creating the stunning patterns seen in telescope images. But how do these models hold up against real-world observations? Scientists have scrutinized the magnetic tower hypothesis by comparing its predictions with data collected from telescopes across the electromagnetic spectrum. For example, X-ray and radio wave observations have revealed elongated structures within the nebula that align remarkably well with the predicted shapes and orientations of magnetic towers. Furthermore, polarized light data, light waves vibrating in a specific direction, have provided evidence of strong, organized magnetic fields emanating from the pulsar. These findings lend support to the idea that magnetic towers are not just theoretical constructs but actual physical features of the nebula. Of course, magnetic tower models are not without their challenges. One lingering question is how these structures sustain themselves over time. Magnetic fields in the nebula are constantly being buffeted by the pulsar's energetic winds and the surrounding turbulent plasma. For the towers to remain stable, they must overcome these disruptive forces, a feat that requires a delicate balance between magnetic pressure and external influences. Researchers continue to refine their simulations to better understand how this equilibrium is achieved and what conditions might cause the towers to collapse or reconfigure. Beyond the Crab Nebula, magnetic tower models hold broader implications for astrophysics. If these structures are indeed confirmed to play a key role in shaping nebulae, they could provide a template for understanding similar phenomena in other cosmic environments. For example, young supernova remnants and active galactic nuclei also exhibit jets and outflows that might be governed by similar magnetic mechanisms. This makes the Crab Nebula not just an isolated wonder, but a microcosm of processes that operate on much larger scales across the universe. As we continue piecing together the evidence, magnetic tower models offer a tantalizing glimpse into the forces driving the Crab Nebula's complex behavior. They remind us that even in the vastness of space, order can emerge from chaos, guided by the invisible hand of magnetism. With this newfound understanding, let's now shift our focus to the pulsar's spin-down power, a phenomenon that lies at the very heart of the nebula's energy dynamics. Stepping into the energetic heart of the Crab Nebula, we encounter a phenomenon that serves as the nebula's cosmic engine, the pulsar's spin-down power. This is the process by which the rapidly rotating neutron star at the center of the nebula gradually loses its rotational energy over time. It's a bit like watching a spinning top slowly wind down, except in this case, the energy being released is on an astronomical scale, fueling the dazzling display we see in the nebula. The pulsar at the core of the Crab Nebula is an incredibly dense object, packing more mass than our Sun into a sphere just a few kilometers wide. As it spins at an astonishing rate of 30 times per second, it emits beams of electromagnetic radiation and generates powerful winds of charged particles. These emissions are not just random bursts of energy, they're directly tied to the pulsar's gradual deceleration, Every second, the pulsar's rotation slows by a tiny fraction, releasing a tremendous amount of energy in the process. This energy output, known as spin-down power, is so immense that it's equivalent to 100,000 times the total energy output of our Sun. What makes this spin-down power so crucial is how it drives the dynamics of the entire nebula. The energy lost by the pulsar doesn't just vanish. It gets transferred into the surrounding environment, powering the nebula's luminosity and shaping its structure. Think of it as the heartbeat of the system, pumping energy outward in the form of high-speed winds and intense radiation. These winds interact with the nebula's gas and dust, creating shock waves that heat the material to millions of degrees and cause it to glow brightly in wavelengths ranging from radio waves to gamma rays. Without this constant infusion of energy from the pulsar, the Crab Nebula would gradually dim and fade away. To truly grasp the significance of spin-down power, consider how it shapes the nebula's dynamics. The energy released by the pulsar creates a feedback loop where the pulsar wind pushes outward against the surrounding material, carving out intricate patterns and structures. For example, the glowing filaments that give the Crab Nebula its iconic appearance are in part a result of this interaction. The pulsar's energy also fuels the jets of particles that shoot out along its rotational axis, which we discussed earlier in the context of magnetic tower models. These jets are not only breathtaking to observe, but also serve as a direct manifestation of the pulsar's spin-down power in action. Interestingly, the connection between spin-down power and the nebula's luminosity offers a way for scientists to study the pulsar's properties indirectly. By measuring the brightness of the nebula across different wavelengths, researchers can estimate how much energy the pulsar is losing over time. This relationship has revealed that the Crab Nebula's central pulsar is one of the most efficient energy converters in the universe, transforming its rotational energy into radiation with remarkable precision. However, there are still mysteries to unravel. For instance, why does the nebula's luminosity occasionally fluctuate? Could these changes be linked to variations in the pulsar's spin-down rate, or are they caused by something else entirely? As we explore these questions, it's worth pausing to appreciate the sheer scale of what we're witnessing. The pulsar at the heart of the Crab Nebula is a powerhouse, converting its rotational energy into a dazzling light show that has captivated astronomers for decades. But it's also a reminder of the intricate balance between chaos and order in the universe. The next phenomenon we'll examine takes us deeper into this interplay, focusing on nonlinear wave propagation and its role in shaping the nebula's ever-changing environment. As we venture further into the complexities of the Crab Nebula, we arrive at a phenomenon that adds yet another layer of intrigue to this cosmic marvel: nonlinear wave propagation. This might sound like a mouthful, but it's essentially about how waves in the nebula behave in ways that defy the simple, predictable patterns we're used to seeing in everyday life. In the chaotic and energetic environment of the Crab Nebula, waves don't always follow a straight path or maintain a steady rhythm. Instead, they interact with each other and their surroundings in surprising and dynamic ways, creating effects that ripple through the entire system. Nonlinear waves are fascinating because they can amplify or distort as they travel, depending on the conditions they encounter. Imagine tossing a pebble into a pond, but instead of neat ripples spreading outward, the waves start to merge, split, or even grow stronger in certain spots. In the Crab Nebula, these waves are not made of water but of electromagnetic energy and charged particles moving at incredible speeds. These waves arise from the pulsar's relentless energy output, creating a maelstrom of activity that constantly reshapes the nebula's structure. One of the most significant impacts of nonlinear wave propagation is how it influences energy transfer within the nebula. As these waves collide and interact, they can redistribute energy across vast distances, sometimes concentrating it in specific regions and other times spreading it out more evenly. This redistribution plays a key role in heating the surrounding gas and dust, keeping the nebula aglow with radiation that spans the electromagnetic spectrum. It's like an invisible hand sculpting the nebula's glowing filaments and clouds, ensuring that no two moments in its existence are ever quite the same. But the influence of nonlinear waves doesn't stop there. They also affect the configuration of magnetic fields within the nebula. Picture these fields as invisible highways guiding charged particles on their journey through space. Nonlinear wave interactions can bend, twist, or even snap these highways, altering how particles move and where they end up. This dynamic reshaping of magnetic fields helps explain some of the nebula's most enigmatic features, such as the bright knots and swirling loops of emission we see in detailed observations. These structures aren't static, they're constantly evolving, thanks in part to the ever-changing interplay of nonlinear waves. What makes this phenomenon particularly challenging for scientists is its unpredictability. Nonlinear systems are notoriously difficult to model because small changes in initial conditions can lead to vastly different outcomes. In the Crab Nebula, this means that even the slightest variation in wave behavior could have significant consequences for the overall dynamics of the system. For instance, a sudden surge in wave intensity might trigger a burst of radiation or create a temporary hotspot that fades as quickly as it appeared. These fleeting events are a reminder of just how alive and active the nebula truly is, pulsating with energy on timescales that are hard to comprehend. Interestingly, studying nonlinear wave propagation in the Crab Nebula offers clues not just about this specific region of space, but about the universe at large. Many of the processes at work here, like energy redistribution, magnetic field reconfiguration, and particle acceleration, are also found in other astrophysical environments, from supernova remnants to distant galaxies. By unraveling the mysteries of the Crab Nebula, researchers hope to develop a deeper understanding of how these processes operate on a cosmic scale. Yet, despite decades of observation and analysis, many questions remain. How do nonlinear waves contribute to the nebula's long-term evolution? Could they hold the key to explaining some of the Crab Nebula's most puzzling phenomena, like its sudden gamma-ray flares? With so much left to discover, the exploration of nonlinear wave propagation in the Crab Nebula opens a window into the intricate dance of forces that govern the universe. And as we continue this cosmic journey, our next stop brings us to a phenomenon that pushes the limits of what we thought was possible: the synchrotron burn-off limit. Here, we'll uncover how particles in the nebula reach their maximum energy and what happens when they exceed it. Now, let's turn our attention to a boundary that governs the energy within the Crab Nebula's most energetic particles, the synchrotron burn-off limit. If you've ever wondered how far the universe pushes its tiniest components, this phenomenon offers a fascinating glimpse into those limits. Essentially, the synchrotron burn-off limit defines the maximum amount of energy that particles can reach before losing that energy just as quickly as they gain it. It's like a cosmic speed check, ensuring that even in the high-energy chaos of the nebula, there's a ceiling beyond which particles simply can't ascend. To understand this, picture electrons spiraling through the nebula's intense magnetic fields. These electrons emit radiation, a process known as synchrotron radiation, as they accelerate along curved paths. The more energy they have, the faster they move and the more radiation they produce. But there's a catch. At some point, the energy they lose through radiation equals or even exceeds the energy being pumped into them by the pulsar's winds. When this happens, the particles hit their peak energy and any further acceleration becomes impossible. This point is what scientists refer to as the synchrotron burn-off limit. The implications of this limit are profound. For one, it helps us understand why we observe certain patterns in the radiation coming from the Crab Nebula. Extremely high-energy photons, those near the upper end of the electromagnetic spectrum, can only be produced by particles operating at their energy limits. So, when we detect gamma rays or other intense emissions, It signals the presence of particles that are right at the synchrotron burn-off threshold. This tells researchers not only about the conditions within the nebula, but also about the underlying physics driving these processes. What makes the synchrotron burn-off limit particularly intriguing is how it helps us refine our understanding of particle acceleration in extreme environments. Think of it as a natural filter. Only particles with just the right balance of energy input and magnetic field strength can emit at these ultra-high levels. Any deviation and the system falls short of reaching the most energetic emissions. This balance offers a powerful tool for testing theories about how particles are accelerated in places like supernova remnants, active galactic nuclei, and even distant cosmic jets. Of course, there's still much we don't know. For instance, what role does the pulsar's magnetic field play in setting this energy cap? Can variations in the field's strength lead to temporary breaches of the synchrotron burn-off limit, creating rare bursts of even higher energy photons? These questions hint at deeper layers of complexity within the Crab Nebula and similar environments across the universe. By studying this limit, scientists hope to uncover not just the secrets of the nebula itself, but also universal principles that govern high-energy astrophysics. As we move ahead, keep in mind that this boundary isn't just a theoretical construct. It's a tangible feature shaping the very structure of the Crab Nebula. And speaking of boundaries, our next stop brings us to relativistic beaming effects, where the nebula's emissions get an extra boost, shining even brighter in certain directions. Moving forward, let's shine a light on a phenomenon that quite literally amplifies the brilliance of the Crab Nebula: relativistic beaming effects. Imagine standing on a cosmic stage where particles traveling near the speed of light put on a dazzling show, their glow intensified in specific directions as if nature itself cranked up the spotlight. This is what happens in the nebula thanks to relativistic beaming, a process that enhances the apparent brightness of emissions when viewed from certain angles. At the heart of this spectacle are the high-speed particles racing outward from the pulsar, particularly within the jets that shoot out like cosmic lighthouses. When these particles move at velocities close to the speed of light, something extraordinary happens. According to the principles of relativity, their emitted radiation gets concentrated and boosted in the direction they're traveling. Think of it as a flashlight beam that becomes brighter and narrower the faster it moves, except in this case, the flashlight is blasting radiation across the universe. What makes relativistic beaming so fascinating is how it tricks our perception. From Earth, we see these emissions as far more intense than they would appear if the particles were stationary or moving slowly. This isn't just a minor effect, it can make the radiation seem thousands of times brighter along the path of motion. Essentially, the nebula's jets and outflows appear to glow with an exaggerated brilliance when viewed head-on, creating a stunning visual effect that astronomers can study to learn more about the underlying physics. But this phenomenon isn't just about looks. Relativistic beaming provides vital clues about the speed and direction of particle flows within the nebula. By analyzing where the brightness spikes occur, scientists can map the structure of the jets and understand how material is distributed and accelerated. It's like using a cosmic magnifying glass to peer into the engine room of the nebula, revealing the machinery that powers its most energetic processes. Interestingly, relativistic beaming isn't unique to the Crab Nebula. It's a common feature in many high-energy environments across the universe, from active galactic nuclei to distant quasars. However, the Crab Nebula offers one of the closest and most detailed laboratories for studying this effect. Its proximity allows researchers to examine relativistic beaming in unprecedented detail, helping to refine models that explain similar phenomena elsewhere in the cosmos. Of course, there's still plenty to unravel. For instance, how does relativistic beaming interact with other forces within the nebula, such as magnetic fields or shock waves? Could temporary changes in the pulsar's activity create fluctuations in the beaming effect, leading to sudden bursts of brightness? These questions keep astronomers coming back for more, eager to piece together the intricate puzzle of the Crab Nebula's workings. As we pull back from the brilliance of relativistic beaming, let's now delve into a more grounded yet equally captivating aspect of the nebula, its dusty embrace. Dust grains within the Crab Nebula hold secrets not just about its past, but also about how such environments influence the formation of stars and planets in their vicinity. Now, let's shift our focus to something that might seem subtle, but is absolutely crucial to understanding the inner workings of the Crab Nebula, how its intricate filaments are heated. These glowing threads, which stretch across the nebula like cosmic cobwebs, aren't just decorative. They're a key piece of the puzzle, and figuring out what heats them gives us deeper insight into the forces shaping this stellar remnant. So, what's powering the warmth in these filaments? Scientists have identified several potential culprits. One leading candidate is shock waves. These powerful surges of energy, created by the pulsar's relentless activity, slam into the filaments and transfer their energy, effectively turning them into cosmic heaters. Think of it like a blacksmith plunging a piece of metal into fire. The shock wave acts as the flame, heating the material until it glows. Another possibility is radiation. The Crab Nebula is a powerhouse of electromagnetic emissions, from X-rays to visible light. This intense radiation bathes the filaments, depositing energy directly into the gas and dust. It's akin to how sunlight warms the Earth's surface, except the energy here is far more intense, capable of heating the filaments to millions of degrees. And then there's conduction, a more indirect but equally important process. Just as heat from a stove spreads through a pot of water, thermal energy from the surrounding plasma can seep into the filaments. This process is subtle but persistent, ensuring that the filaments maintain their glow even in the absence of direct shocks or radiation. What makes this phenomenon so intriguing is that it's likely not just one mechanism at play, but a combination of all three. Each contributes in its own way, creating a dynamic interplay of forces that keeps the filaments aglow. By studying how these mechanisms interact, scientists can piece together a more complete picture of the nebula's energy flow and its overall behavior. But here's the kicker: understanding filament heating isn't just about the Crab Nebula itself. These processes offer clues about other nebulae and even galaxy formation. After all, filaments are a common feature in many cosmic environments, and the lessons we learn here could unlock secrets far beyond our own little corner of the universe. With these insights in mind, let's now turn our attention to another fascinating aspect of the Crab Nebula: how particles manage to escape its grasp and venture out into the vastness of interstellar space. As we venture further into the enigmatic heart of the Crab Nebula, there's another cosmic mystery that demands our attention: how particles manage to break free from its grasp. This phenomenon isn't just about particles slipping away. It's a delicate dance between confinement and liberation, offering us clues about the nebula's interaction with its surroundings. So, let's explore how these tiny cosmic travelers make their grand exit and what that reveals about the forces at play. To understand particle escape rates, we first need to grasp the concept of confinement timescales. Picture the nebula as a bustling cosmic city with particles zipping around like busy citizens. Some of these particles are confined within the nebula's magnetic and gravitational boundaries, held in place by the pulsar's powerful influence. But not all of them stay put. Over time, a fraction of these particles gain enough energy to escape, venturing out into the vast expanse of interstellar space. The rate at which this happens is linked to how long particles can remain trapped before external forces nudge them out. Now, what exactly helps these particles break free? One key factor is the turbulent environment within the nebula itself. The same shock waves and magnetic instabilities that heat the filaments also stir up the plasma, creating conditions where particles can accelerate to incredible speeds. When these particles reach velocities high enough to overcome the nebula's magnetic grip, they essentially punch their ticket to freedom. It's a bit like a roller coaster building momentum until it finally rockets out of its track, except here the stakes are cosmic. Another important element is the interaction between the nebula and the interstellar medium. Think of the interstellar medium as an ocean and the Crab Nebula as a whirlpool within it. As the nebula expands, its outer edges push against this surrounding ocean of gas and dust. This interaction can create pathways for particles to escape, like water spilling over the edge of a bowl. These escaping particles don't just disappear, though. They carry energy and information with them, seeding the interstellar medium with traces of the nebula's activity. What makes this phenomenon particularly fascinating is how scientists use it to study the nebula's life cycle. By measuring the escape rates of particles, researchers can estimate how long the nebula has been active and how much energy it's pumping into its surroundings. This data also helps paint a clearer picture of how supernova remnants like the Crab Nebula contribute to the cosmic ecosystem, enriching the interstellar medium with heavy elements and high-energy particles. But here's where it gets even more intriguing. The particles that escape the Crab Nebula don't just drift aimlessly. They become part of a much larger cosmic narrative, influencing everything from the formation of new stars to the behavior of galactic magnetic fields. In a way, these tiny escapees serve as cosmic ambassadors, carrying the story of their origins far beyond the boundaries of their birthplace. As we piece together the puzzle of particle escape rates, we're left with a deeper appreciation for the interconnectedness of the universe. Every particle that leaves the Crab Nebula is a thread in the grand tapestry of space, linking this distant stellar remnant to the broader cosmos. And speaking of connections, our next stop on this cosmic journey takes us into the realm of magnetic loop structures, where stability and energy storage create yet another layer of mystery within the nebula's dynamic heart. Now, let's turn our attention to another captivating feature of the Crab Nebula: its intricate network of closed magnetic loops. These structures might sound like something out of a science fiction novel, but they're very real and play a vital role in shaping the nebula's behavior. To understand them, imagine a series of invisible hoops woven throughout the nebula, each one pulsing with energy and holding secrets about how the cosmos stores and releases power. Magnetic loops are essentially arches of magnetic field lines that form closed circuits within the nebula. These loops are created by the intense magnetic fields generated by the central pulsar, which acts like a cosmic dynamo. What makes them so fascinating is their stability, or at least the illusion of it. While they might seem static, these loops are anything but still. They're constantly being stretched, twisted, and reshaped by the turbulent environment around them. This dynamic interplay raises an important question. How do they maintain their structure amidst such chaos? One reason these loops remain stable, at least for a time, is their ability to trap charged particles. Think of these loops as cosmic pinball machines, where particles bounce back and forth between the magnetic field lines. This confinement not only helps the loops retain their shape, but also turns them into reservoirs of energy. The particles spiraling within these magnetic loops radiate energy in the form of synchrotron radiation, which contributes to the nebula's dazzling glow. But that's not all. They also store vast amounts of energy, like coiled springs waiting to release their tension. This energy storage mechanism is crucial for understanding how the Crab Nebula sustains its luminosity over time. The loops act as buffers, regulating the flow of energy from the pulsar to the surrounding nebula. When these loops finally destabilize, a process that can happen suddenly, they unleash bursts of energy that ripple through the nebula, creating spectacular displays of light and radiation. It's akin to a dam bursting, flooding the surrounding area with pent-up power. These events might even explain some of the sudden flares and bursts of activity that astronomers have observed in the nebula. But what causes these loops to destabilize in the first place? The answer lies in the same forces that give them their initial stability. The interplay between magnetic fields, shock waves, and the relentless push of the pulsar's wind can create imbalances within the loops. Over time, these stresses build up until the loops can no longer contain the energy, leading to dramatic releases that reshape the nebula on both small and large scales. It's a delicate balance, one that highlights the ever-changing nature of the Crab Nebula's environment. The study of magnetic loop structures doesn't just deepen our understanding of this particular nebula, it offers broader insights into how magnetic fields shape the universe. Similar structures have been observed in other astrophysical environments, from the Sun's corona to distant galaxies. By unraveling the mysteries of these loops in the Crab Nebula, scientists hope to uncover universal principles about energy storage and release in magnetic systems. As we marvel at the complexity of these magnetic loops, we're reminded that the Crab Nebula is more than just a stellar remnant. It's a living laboratory where the forces of nature are on full display. And speaking of forces, our next phenomenon takes us deeper into the chaotic heart of the nebula, where turbulence plays a starring role in shaping its dynamic gas clouds. As we venture further into the heart of the Crab Nebula, we encounter yet another fascinating process that shapes its ever-changing landscape, the growth of thermal instabilities. These instabilities might sound like something out of a science experiment, but they're actually key players in the nebula's dynamic evolution. To understand their role, picture a vast cloud of gas floating in space, seemingly calm on the surface. But beneath that calm exterior, tiny fluctuations in temperature and density begin to take hold, setting off a chain reaction with remarkable consequences. Thermal instabilities occur when certain regions within a gas cloud cool down more quickly than others. This cooling causes the gas in those areas to become denser, and as it compresses, it becomes even cooler. It's a feedback loop where cooler regions grow denser and denser regions grow cooler, creating pockets of gas that stand out from their surroundings. Over time, these pockets can fragment the once uniform cloud into smaller, clumpy structures. This process is akin to how water vapor condenses into droplets, forming clouds in Earth's atmosphere, but on a cosmic scale. The role of these instabilities in the Crab Nebula is particularly intriguing because they help explain the formation of dense knots, those concentrated clumps of material scattered throughout the nebula. These knots, which can be several times denser than their surroundings, are thought to form as thermal instabilities cause gas clouds to break apart and collapse under their own gravity. Once formed, these knots become sites of intense activity, often glowing brightly as they interact with the surrounding radiation and magnetic fields. They're like cosmic building blocks, shaping the nebula's structure in ways that scientists are still working to fully understand. But the influence of thermal instabilities doesn't stop at fragmentation. These processes also play a part in mixing materials within the nebula. As the gas clouds break apart, they create turbulence, stirring up the surrounding environment and redistributing elements like hydrogen, helium, and heavier metals. This mixing is crucial because it affects how the nebula evolves over time, influencing everything from its chemical composition to its overall appearance. It's a reminder that even in the vastness of space, small-scale processes can have big-picture effects. What makes thermal instabilities so captivating is how they highlight the delicate balance between order and chaos in the Crab Nebula. On one hand, they're driven by simple physical principles: cooling, compression, and gravity. On the other hand, their outcomes are anything but predictable. The knots they create can vary widely in size, density, and behavior, contributing to the nebula's intricate and ever-shifting tapestry. Scientists are particularly interested in studying these knots because they offer clues about the conditions within the nebula and how energy flows through it. As we continue to explore the mysteries of the Crab Nebula, it's clear that thermal instabilities are more than just a footnote in its story. They're a testament to the complex interplay of forces that govern the universe, shaping everything from the smallest gas clouds to the grandest cosmic structures. And speaking of cosmic structures, our next phenomenon takes us deeper still, where the alignment of dust grains reveals even more about the invisible forces at work in this extraordinary region of space. Now, let's shift our focus to a phenomenon that adds yet another layer of intrigue to the Crab Nebula time domain fluctuations. These fluctuations might sound like something out of a sci-fi novel, but they're very real and offer profound insights into the nebula's behavior. To put it simply, time domain fluctuations refer to changes in the brightness or intensity of the nebula's emissions over time. What makes these fluctuations so fascinating is that they occur on timescales that range from mere fractions of a second to several hours or even days. Imagine standing under a flickering street lamp at night. Sometimes the light dims, other times it brightens, seemingly without a clear pattern. Now, imagine that same flickering happening across an entire region of space, with light and energy pulsing in ways that defy easy explanation. That's essentially what scientists observe when they study the Crab Nebula's emissions. These fluctuations are not random in the way we might think, though. They hint at deeper processes at play, processes that could involve everything from chaotic turbulence within the nebula to hidden variables we have yet to fully understand. There are two main theories that scientists use to explain these fluctuations. The first points to stochastic processes, which are essentially random events that occur without a predictable pattern. In the context of the nebula, this could mean that the fluctuations arise from the chaotic movement of particles, magnetic fields, or even shock waves colliding within its structure. Think of it like ripples spreading across a pond after you toss in a handful of pebbles. Each ripple interacts with others in unpredictable ways, creating a complex and ever-changing pattern. The second theory suggests that the fluctuations might be influenced by hidden variables, factors that we can't directly observe but that subtly shape the nebula's behavior. These could include variations in magnetic field strength, unseen pockets of dense material, or even the influence of the central pulsar. It's a bit like trying to understand the mood of a room by observing only the shadows on the walls. You might catch glimpses of movement or shifts in tone, but the full picture remains elusive. What's particularly captivating about time domain fluctuations is how they challenge our understanding of cosmic environments. On Earth, we're used to predictable patterns like the steady glow of the sun or the reliable rhythm of the tides. But in the Crab Nebula, nothing is constant. The fluctuations suggest a dynamic and restless environment where energy and matter are in constant motion, interacting in ways that we're only beginning to unravel. One of the most exciting aspects of studying these fluctuations is the technology behind the observations. Advanced telescopes and detection instruments allow scientists to capture changes in the nebula's emissions with incredible precision. This has opened a window into processes that were once invisible, helping us piece together a more complete picture of the nebula's inner workings. And yet, for all we've learned, these fluctuations remind us that the universe is still full of mysteries waiting to be solved. As we wrap up this look at time domain fluctuations, it's worth noting how they connect to other phenomena we've explored, like the nebula's turbulent gas dynamics or the influence of its magnetic fields. Together, these processes paint a picture of a cosmic region that's anything but static, a place where energy, matter, and time itself seem to dance in an intricate and ever-changing rhythm. And speaking of rhythms, our next phenomenon takes us even deeper into the heart of the Crab Nebula, where the alignment of dust grains offers new clues about the invisible forces shaping this extraordinary cosmic laboratory. Moving forward, let's uncover a phenomenon that feels almost otherworldly in its precision: dust grain alignment within the Crab Nebula. This might sound like an obscure or niche topic, but it's actually a cosmic detective story that reveals how invisible forces shape the universe around us. At the heart of this mystery are tiny particles of dust scattered throughout the nebula. These grains, though minuscule, hold immense clues about the magnetic fields and radiative forces at play. When scientists study the Crab Nebula, they notice something peculiar about these dust grains. They aren't oriented randomly. Instead, they appear to align in specific patterns, creating a kind of cosmic order within the chaos. Imagine walking into a forest where every tree is leaning in the same direction, not because of wind, but because of some unseen force guiding them into position. In the case of the nebula, it's the magnetic fields and radiative torques that act as this guiding force, influencing how the dust grains arrange themselves. To understand this better, let's break it down. Magnetic fields are like invisible highways stretching across space and influencing the movement of charged particles. When dust grains interact with these fields, they tend to line up along the field lines, much like iron filings aligning around a magnet, but that's not the whole story. Radiative torques, essentially the push and pull created by incoming light and radiation, also play a critical role. Think of it as sunlight hitting a weather vane, causing it to turn and point in a specific direction. Together, these forces work in tandem, creating alignment patterns that scientists can detect and study. What makes this phenomenon so fascinating is the window it opens into the nebula's invisible architecture. Magnetic fields are notoriously difficult to observe directly, but by studying how dust grains align, researchers can map out the field's direction and strength. It's a bit like using shadows to deduce the shape and position of an object blocking the light. These alignment patterns tell us not only about the magnetic fields themselves, but also about the interplay between radiation and matter within the nebula. Interestingly, this alignment isn't just a static feature. It's dynamic, shifting as the magnetic fields change or as radiation levels fluctuate. This adds another layer of complexity to the Crab Nebula's already intricate behavior. For instance, if a burst of high-energy radiation sweeps through the region, it could alter the alignment of the dust grains, creating a ripple effect that scientists can track over time. It's like watching a symphony where every note influences the next, revealing the underlying harmony of the cosmos. The implications of dust grain alignment extend beyond the Crab Nebula itself. By studying this phenomenon, scientists gain insights into how magnetic fields and radiation shape other regions of space, from stellar nurseries to distant galaxies. It also raises questions about the role of dust in the universe. Could these tiny particles, often overlooked, actually be key players in the grand cosmic drama? It's a humbling thought that something so small could have such a profound impact. As we marvel at the alignment of dust grains, it's worth noting how this phenomenon ties into the larger tapestry of the Crab Nebula's mysteries. From the turbulence of its gas dynamics to the flickering of its time domain fluctuations, every piece of the puzzle helps us understand this extraordinary region. And as we prepare to delve into the next phenomenon, electron gyration frequencies, we'll continue to peel back the layers of this cosmic enigma, one discovery at a time. Now, let's shift our gaze to a phenomenon that acts as a kind of cosmic metronome, setting the rhythm for the Crab Nebula's hidden forces, electron gyration frequencies. These frequencies might sound like something out of a science fiction novel, but they're actually a powerful tool scientists use to uncover the secrets of magnetic fields within the nebula. To put it simply, when electrons are trapped in a magnetic field, they don't just float aimlessly. Instead, they spiral around the magnetic field lines like tiny dancers tracing invisible loops in space. The rate at which these electrons gyrate or spin is directly tied to the strength of the magnetic field they're moving through. Think of it like a spinning top. Its speed depends on how much force is applied. In this case, the magnetic field acts as the force dictating the pace of the electron's motion. By measuring these gyration frequencies, researchers can essentially reverse engineer the magnetic field's properties. It's akin to listening to the hum of a guitar string and figuring out how tightly it's been tuned. What makes this process so fascinating is how it bridges the gap between the observable and the invisible. Magnetic fields are notoriously difficult to study directly because they don't emit light or radiation on their own. But electrons, as they zip and whirl in response to these fields, act as natural probes, broadcasting subtle signals that can be detected with advanced instruments. These signals provide a treasure trove of information about not only the strength of the magnetic field, but also its shape and structure. For instance, if the magnetic field is uniform and steady, the gyration frequencies will reflect that consistency. But if the field is chaotic or turbulent, the electrons will behave erratically, their frequencies shifting in response to the field's fluctuations. This interplay gives scientists a dynamic snapshot of the magnetic environment within the Crab Nebula, revealing details that would otherwise remain hidden. Interestingly, electron gyration frequencies also help us understand how energy is distributed throughout the nebula. When high-energy particles interact with magnetic fields, they emit radiation, much of which we can detect as light or other signals. By studying these emissions alongside the gyration frequencies, researchers can piece together a more complete picture of the energy flow within the nebula. It's like watching the inner workings of a vast cosmic engine where every component plays a critical role. This phenomenon doesn't just deepen our understanding of the Crab Nebula, it also has far-reaching implications for astrophysics as a whole. Magnetic fields are everywhere in the universe, shaping everything from the formation of stars to the behavior of galaxies. By using electron gyration frequencies as a probe, scientists can refine their models of these fields, improving our ability to study distant and often mysterious regions of space. As we explore the intricacies of electron gyration frequencies, we're reminded of how interconnected the phenomena in the Crab Nebula truly are. From the alignment of dust grains to the dynamic motion of charged particles, every detail contributes to the larger cosmic puzzle. Up next, we'll examine shock heating efficiency, a process that sheds light on how energy is transferred and transformed within this ever-evolving stellar remnant. Together, these phenomena paint a picture of a region that's as complex as it is awe-inspiring. Having explored the intricate behaviors of particles and magnetic fields within the Crab Nebula, we now turn our attention to the bigger picture, the evolutionary journey of this iconic supernova remnant. To truly appreciate the Crab Nebula in its current form, we need to rewind the cosmic clock and revisit the explosive event that gave it life. Roughly 960 years ago, a massive star in the constellation Taurus met its spectacular end in a brilliant supernova explosion. This cataclysmic event not only lit up the night sky, but also scattered elements forged in the star's core across the surrounding space, creating the foundation for what we see today. The Crab Nebula, as we know it now, represents a snapshot of the aftermath. Over the centuries, the debris from that explosion has been expanding outward, pushed by the force of the blast and shaped by the intense energy still emanating from its central pulsar. This expansion isn't uniform, though. The nebula's outer edges interact with the interstellar medium, the sparse material that fills the space between stars. These interactions create complex patterns and slow down the expansion in some areas, offering clues about the environment surrounding the nebula. By studying these dynamics, scientists can piece together how the nebula has evolved and predict how it might change in the future. What makes the Crab Nebula particularly fascinating is that it's still very much an active region of space. The central neutron star, also known as a pulsar, continues to pump vast amounts of energy into the surrounding material. This energy keeps the nebula glowing brightly and drives many of the strange phenomena we've explored, from synchrotron radiation to high-energy gamma-ray flares. In essence, the pulsar acts like a cosmic powerhouse, maintaining the nebula's vibrant appearance and dynamic behavior. Interestingly, the Crab Nebula is considered a relatively young supernova remnant. In cosmic terms, 960 years is barely the blink of an eye. Comparing it to older remnants gives us valuable insights into the life cycle of these stellar remnants. For instance, older remnants tend to fade over time as their energy dissipates and their expansion slows. The Crab Nebula, however, shows no signs of fading anytime soon. Its pulsar remains extraordinarily energetic, and the nebula's intricate structures continue to evolve, offering scientists a front-row seat to the processes shaping the universe. This ongoing evolution also raises intriguing questions about the nebula's future. Will it continue to expand indefinitely, or will it eventually slow and fade as it blends into the interstellar medium? Will the pulsar's energy output remain steady, or could it undergo sudden changes that alter the nebula's behavior? Each of these possibilities underscores the dynamic nature of the Crab Nebula, reminding us that even seemingly stable cosmic objects are in constant flux. As we reflect on this remarkable journey from supernova explosion to the present day, we gain a deeper appreciation for how the Crab Nebula serves as a living laboratory for astrophysics. It connects past events to current phenomena, offering a window into the forces that govern the universe. And yet, there is still much to uncover, particularly when it comes to the amplification of magnetic fields within this enigmatic structure. Let's now delve into one of the most puzzling aspects of the Crab Nebula: how these magnetic fields grow stronger over time, shaping the environment in ways we're only beginning to understand. Moving forward, let's unravel one of the most intriguing puzzles within the Crab Nebula: the amplification of its magnetic fields. This phenomenon is not just a curiosity, but a key piece in understanding the forces that shape this cosmic powerhouse. Magnetic fields are invisible yet incredibly influential, dictating how particles move and energy flows throughout the nebula. But how do these fields grow stronger over time? Scientists have proposed several mechanisms, each offering a glimpse into the dynamic processes at play. One leading explanation points to turbulence. Think of turbulence as the chaotic swirling of cosmic winds within the nebula. As particles and gas move unpredictably, they stretch and twist magnetic field lines, much like pulling on a tangled thread. This stretching action intensifies the magnetic field, concentrating its strength in certain areas. It's a bit like crumpling a piece of paper. The more you squeeze, the tighter and more compact it becomes. In the case of the Crab Nebula, this turbulence-driven amplification could be responsible for the highly ordered magnetic structures we observe. Another mechanism involves compression. As the expanding debris from the supernova collides with the interstellar medium, the outer edges of the nebula experience intense pressure. This compression squeezes the magnetic field lines closer together, boosting their strength. Imagine pressing down on a sponge. The harder you push, the more concentrated the material becomes. In the same way, the interaction between the nebula's outer layers and its surroundings could be enhancing the magnetic field, creating regions of heightened energy. These processes not only amplify the magnetic field, but also influence the nebula's behavior on a larger scale. For instance, stronger magnetic fields can accelerate particles to near light speeds, contributing to phenomena like synchrotron radiation and gamma-ray flares. They also play a role in shaping the nebula's filamentary structures, guiding the movement of charged particles and influencing how gas and dust are distributed. In essence, the magnetic field acts as a hidden architect, crafting the nebula's intricate design. What makes this amplification even more fascinating is its potential connection to other cosmic environments. Magnetic fields are a universal force shaping everything from galaxies to black holes. By studying how they grow stronger in the Crab Nebula, scientists gain insights that could apply to other regions of the universe. Could similar mechanisms be at work in distant supernova remnants or even in the early universe itself? These questions highlight the importance of the Crab Nebula as a natural laboratory for astrophysics. As we continue this cosmic journey, the interplay between magnetic fields, particles, and energy remains a central theme. With this understanding of magnetic field amplification in mind, our exploration now shifts to the pulsar's role in powering the nebula's luminosity and dynamics. This connection reveals yet another layer of complexity, offering fresh insights into the forces that sustain this extraordinary celestial object. As we reach the final frontier of our exploration into the Crab Nebula's mysteries, it's time to turn our gaze toward the horizon of discovery. The phenomena we've uncovered so far paint a picture of a cosmic masterpiece, but many questions remain unanswered, waiting for future astronomers and technology to unravel their secrets. What lies ahead is not just a challenge but an invitation, an opportunity to push the boundaries of what we know about this enigmatic region of space. One of the most pressing unresolved questions revolves around the pulsar's true influence. While we've discussed its role in powering the nebula, the exact mechanisms that govern its interaction with surrounding particles and magnetic fields are still not fully understood. How does the pulsar maintain such a precise and powerful output of energy over thousands of years? Could there be hidden processes at play that we haven't yet detected? These questions underscore the need for more sensitive instruments capable of probing the pulsar's emissions in greater detail. Another challenge lies in observing the nebula's faint outer regions. Much of what we've studied focuses on its brighter, more dynamic core, but the edges of the Crab Nebula hold clues about its interaction with the interstellar medium. Mapping these distant areas in multiple wavelengths could reveal how the nebula is evolving and whether external forces like nearby stars or gas clouds are shaping its future. However, detecting such faint signals requires advancements in telescope technology and data analysis techniques. There's also the question of time. Many of the phenomena we've explored, from gamma-ray flares to magnetic field amplification, occur on timescales that are difficult to capture with current observations. Developing instruments that can monitor the nebula continuously, or at least over extended periods, would allow us to catch fleeting events and piece together a more complete picture of its behavior. This is no small feat given the vast distances and energies involved, but it's a challenge worth pursuing. As scientists continue to refine models of the Crab Nebula, they'll also need to test these models against new data. Simulations have been invaluable in understanding phenomena like shock waves and particle acceleration, but they're only as good as the observations they're based on. Future missions, perhaps involving space telescopes or even interstellar probes, could provide the breakthroughs needed to validate or refine these theories. Imagine the insights we could gain from sending a probe closer to the nebula, capturing data directly from its chaotic environment. And let's not forget the broader implications of studying the Crab Nebula. What we learn here could reshape our understanding of other supernova remnants and even the early universe. Is the Crab Nebula a unique cosmic anomaly, or does it share features with similar objects across the cosmos? Answering these questions could help us piece together the story of how stars live, die, and influence the universe around them. So, as we conclude this journey, remember that the Crab Nebula is more than just a stunning astronomical object. It's a living laboratory, a playground for discovery, and a reminder of how much there is still to learn. The mysteries we've explored today are just the beginning, and the next big breakthrough could be closer than we think. Keep looking up, stay curious, and who knows? Maybe one day you'll be part of the team that unlocks the secrets of this extraordinary corner of the universe. If you enjoyed this cosmic adventure, don't forget to subscribe, hit the notification bell, and share your thoughts in the comments below. The universe is waiting, and there's always more to explore. As we bring this cosmic journey to a close, let's take a moment to reflect on the wonders we've uncovered. From the pulsar's relentless energy to the dazzling dance of particles and magnetic fields, the Crab Nebula has proven itself to be a treasure trove of strange and captivating phenomena. Each of the 50 mysteries we've explored adds a new layer to our understanding of this stellar remnant, yet they also remind us how much remains hidden in the vastness of space. It's a place where science meets imagination, where every observation brings us closer to unraveling the secrets of the universe. The Crab Nebula isn't just a relic of a star's explosive past, it's a living, breathing laboratory, offering insights into the life cycles of stars, the behavior of cosmic particles, and the forces that shape our galaxy. What we learn here doesn't just apply to this single object. It echoes across the cosmos, helping us piece together the story of how stars influence the universe long after their fiery deaths. Whether it's the unexpected gamma-ray flares, the intricate filamentary structures, or the enigmatic magnetic fields, every discovery underscores the importance of curiosity and persistence in the pursuit of knowledge. But the story doesn't end here. The Crab Nebula still holds countless secrets, waiting for the next generation of telescopes, missions, and curious minds to reveal them. Perhaps one day we'll develop the tools to explore its chaotic heart up close, capturing data that could transform our understanding of the universe. Until then, let this celestial wonder inspire you to look beyond the horizon, to question the unknown, and to dream of possibilities beyond our reach. If this cosmic adventure has sparked your curiosity, don't forget to subscribe for more explorations into the mysteries of the universe. Hit the notification bell to stay updated and share your thoughts in the comments. What phenomenon fascinated you the most? The universe is vast and there's always more to discover. Keep watching, keep wondering, and together, let's continue this journey into the